Alright, hey guys. Let's see. I remember last time we had audio problems, so if you can hear me, that'd be ideal. See if that will work. So I know it usually says that the microphone is working, and then sometimes it just doesn't. So let me see. Is there still no audio? Okay, wait. Like when I do that, let me fix something else then. Did that work? Okay, it does work. Alright, cool. Okay, so the audio is ready. Are you all ready to learn some graphs? Hopefully I would be because I'm teaching it, so that's sort of important. And I will, let me see, do the standard stuff, Discord. And click some stuff. Very prepared, as always. Actually, in fact, I'm not prepared at all because I don't even have my files open. So let's do that first. I don't know what's been up this morning, but my voice is a bit weird, so bear with me. Yeah. So, we have a topic string, and we're doing graphs. So, I should probably get into a bit of introduction since this is sort of a theory-based topic. With that being said, I will do that right now. So let's just like start with the basics. What is a graph? Let me get my trusty set up so I can read the chat at the same time. So what is a graph? Well, a graph is, like some graph G, is some set of vertices and edges. Now, a vertex is sort of hard to define. It doesn't really have any like actual meaning. It's just sort of like, you can think of it in many different ways, like a point, for example. Like you have a point in space or something. Oftentimes we represent vertices as something like cities and then, or locations. And then to use these vertices, we create relations between them called edges. So for example, we can have an edge between these two vertices. And the meaning of an edge also depends on how you want to define it. But for example, given the context of cities, you can say that this edge between these two cities means that there's some sort of connection between them. Like for example, you can take a plane between these two cities. That's often how it's used. So yeah. Right, now it's sort of like a sort of a meaningless definition. I haven't really said much. And the reason is that like the basic definition of a graph doesn't really have much to it. What's sort of important is what you can do with these things. So yeah. So again, vertices are just points. That's all they really are. And then edges are connections between points somehow. So I can start listing these off. Points and edges. I'll use better colors. And then edges are like connections. Right, now if I draw a few more edges, then we can start defining some more things. So a path is where things start to get useful. So a path is just like a sequence of vertices. So for example, a path could start here, and then it would go to this vertex, and then it would go to this vertex. And so the necessary component for a path is that in every vertex in the sequence of vertices, you have to have an edge between like at each point, to go from one vertex to another, you have to have an edge between them. So a path is sort of like starting at a vertex and then going along some edges until you reach some final vertex. So it's like a sequence of vertices connected by an edge. See, again, if we think of edges as connections, then it's sort of like the edges are connecting these things, and we have to take paths using edges. But we can't like have a path between two vertices that aren't directly connected to each other by an edge. For example, I can't go here and then here, because even though there is a sequence of edges that connects these two, it's more than one. There's no direct edge between these two vertices, so that's not possible. Yeah, but that's fine. It's not that necessary. So, right. So we can say that two vertices are like directly connected if there's an edge between them. So these would not be because there's no edge between them, but these would be. And then we can say that two vertices are generally connected. Like these two vertices would be connected. And the reason is that because you can get from one to another. Like there's like two vertices will be connected if you can simply get between them. If there's some path between them is a better way to define it. So two vertices are connected if there's a path between them. At the early stages, I'm just listing off definitions because I'm not really sure what else to do. It's just sort of like, this is the necessary introduction to things. So two vertices are connected if there exists some path between them. So for example, these two vertices would not be. These two vertices would not be because there's no sequence of edges you can take to get from this one to this one. They simply aren't connected. Whereas every vertex in this group I've encircled in red will be connected to every other vertex. And so the idea of a lot of vertices being connected to each other inspires something else, which is called connected components. And so a connected component is simply a group of vertices where all of the vertices in the group are connected. So for example, these four will form a connected component because every vertex in this 4 is connected to some other vertex in that group. It's not necessarily adjacent. There's no direct edge between, for example, these two, but they're connected because I can take a path between them. And similarly, this lonely vertex also forms a connected component. So anyway, that is enough for this. So a connected component is a group of vertices where all are connected. I'm writing it down because some people prefer that. Right. So again, these two are components. Anyway, components are very sort of useful because they have a lot of things to do with each other. For example, say I wanted to give you some queries. Like say I wanted to say, here's a vertex, here's another vertex, tell me if they're connected. So what we can do is, one possible thing we can do is we can start from this vertex and then we can start going through the edges and we can start going through the edges and then we can look at all of the vertices that this vertex is connected to. So for example, we can take this edge and then we know that this vertex here is connected to this one because we just took an edge to get there. And similarly, if we go here and we take this edge, we know that these two are connected because we just took an edge to get here. And then here, well, we just found this vertex, so we're done, but we can even keep going. We could look at every other edge that's adjacent to some node we've already visited and say, hey, look, we just took an edge to get here, so now we can reach here too. This is like the very like a very basic low level or very basic high level form of DFS or BFS, but don't worry about that yet. But say we somehow knew how to find connected components, then we know that it's a group of vertices where all of them are connected. So, like, say we have a query for two vertices and we're asking if they're connected to each other. That is there a path between them? Well, if they're in the same connected component, then we know they're in the same group, and every pair of vertices in this group is connected. So if we have two vertices in the same connected component, we know they're connected. And conversely, I guess that's the right word. If we ask for two nodes that are in different components, I mean, look at this. If these two nodes were connected to each other, then they would be in the same connected component, because we'd be able to reach to here from here, and we can reach every other vertex in this component can reach this one by definition. So if this one can reach this one, then all the other ones can reach this one as well. So we sort of reach a contradiction that if two vertices are in the same connected component, if two vertices are in different connected components, then they can't be connected, because if they were, then we could increase the size of the connected component. We could sort of merge these two. But we assume we can't do that. So one of the things with checking connected components is that we assume we make them as large as possible. So for example, if I have these things, if I have these vertices that are sort of like this, I say this is here and then this is here, then like I wouldn't make these two connected components and then totally ignore this edge, because these are connected to each other. We can make these components larger, so we would want to make the whole thing at one component. So we make connected components as large as possible, and that way this sort of query thing works. If two edges are in the same component, or if two vertices are in the same component, we automatically know they're connected by definition. And if not, then we know they aren't. So anyway, that's a sort of basic utility of graphs. But I think doing problems will sort of help sort of solidify this idea. So these are some definitions. If you happen to want to take a screenshot, that's fine, although you can also rewind, and I'm not exactly sure how helpful it'll be to just list these off anyway. So it's not that necessary. I will leave this page up though, and then we can play with it a bit later. So let's see. Strongly connected. Yes, there are also, so the way I drew this graph is sort of like edges sort of go both ways. That an edge between these two vertices means that this can go here and this can go here. But there also exists a variant called directed graphs, where an edge is only one way. So for example, like this. So I can go here, but I can't go here because it's directed. So these directed graphs bring up a lot of new different things. Oh, and this graph is called undirected. Every edge goes both ways. So these directed graphs bring up new things. For example, like all the connected components, it's sort of weirder to define, because like, for example, so I do this, so I have this directed graph. I can get from here to everywhere, and I can get from here to here, but I can't get anywhere from here. So some things can reach all the other ones, but some things can't. So we define it, so there's another thing called a strongly connected component, but I'll save that for later, for now. Yeah. So don't worry about strongly connected components yet. We'll handle that later. Anyway, yeah, I do have a practice contest. This should be here if you click the description. Yeah. Okay, anyway. I don't have much more to say about graphs. Perhaps there's some other stuff I missed, but let's see. Chat is mostly saying hello. Yeah, hello everyone. A bit late, like 10 minutes late, but can't hurt to do it. But yeah, if you go to the description, then you can this invitation link should work if you have an account, so you can click on that. Also, I have a few more links, like my code templates and stuff. Although I'm gonna try and write everything from scratch for this stream, so we'll have fun with it. All right, so I'm going to start at A. Usually I pin the comment. What am I sipping? I'm not drinking anything. Maybe water usually, sometimes. I just have like a big water bottle that lasts me a while. Okay, so we're gonna get started with the problems. And once again, I linked the original problem source in case you want to like see difficulty or the editorial or things like that. So, New Year's coming in line world. In this world, there are n cells numbered by integers from 1 to n as a 1 by n board. So what does that look like? It means we have a bunch of gaps here, for example, like cells. Let's see. What do they have? They have 8. That's a lot. Okay. So we have n cells as a 1 by n board. People live in cells. However, it's hard to move between distinct cells because of the difficulty of escaping the cells. People wanted to meet people who live in different cells. So, some user, with a name with all consonants, so that's not a good thing to pronounce, has made a transportation system to move between these cells to celebrate the New Year's. First, he thought of n-1 positive integers. Okay. For every integer I that's not n, so for example, for every integer I in this range, the constraint ai is between 1 and n-I. Okay, so what does that mean? Like, what does it mean for this constraint to exist? Well, what matters is what it means with the rest of the problem. So next he makes n+1 portals numbered by integers from 1 to n+1. The ith portal connects cell I and cell I plus ai. So for example, say we have these numbers. Let's write these down. So we have 1, 2, 1, 2, 1, 2, 1. So, for example, the portal at cell 1 will connect cell 1 and cell 1 plus A1, and A1, so 1 is connected to 1 plus A1, and A1 is equal to 1, so this is 2. So this will connect cell 1 to cell 2. It also says that, wait, why am I messing this up? Did I just delete this? Okay, I don't know what's going on. It connects cell 1 and 2. However, it also says that you can't go backwards. So you can only go forward. Like, this only connects 1 to 2. It's a directed edge. And now this constraint sort of makes more sense now, that it basically means that the portal can't go further than n. So for example, say I'm at 5. Then n minus 5 is 8 minus 5 is equal to 3. So it means that I can't go further than 3 forward, because if I could, then I can go like off the map, and that's dumb. So that's all this constraint means. It just means that like a portal won't take us off the map. So anyway, let's draw the rest of these connections. So this will connect to here. This will also connect to here. This will connect to here. This will connect to here as well. And these will both connect to the end. So the idea is like, this is sort of an involved graph. It's sort of a bit hard to follow. But the idea here is we're at 1. We want to figure out, we have some cell t. What do they have? So t equals 4. So we have some cell t. And we want to figure out if we can use these portals to get to cell t. So in itself, this is sort of a rather simple problem, because at every point, there's only one point where you can go. You can only go to wherever the portal takes you. So either you stay here, or you take the direction of the portal. And so because every portal moves you at least 1 to the right, like we can just simulate going through the portals until we reach the end. And this will take at most O of n time, because every portal is sort of just done. So yeah. So in a graph context, this is simply adding a bunch of directed edges. Then we're interested in then like in the sort of like graph context, we're interested in, does there exist a path between vertex 1 to vertex t in this directed graph where the portals form edges? So is there a path from 1 to t? That's what we're asking. Right? Because a path is just a sequence of connected vertices. So can we get from 1 to t? Is there a path between them? So yeah, this is not that bad because there's no actual graph knowledge necessary for this. I just had this as an introduction so you can start sort of trying to see like how graphs appear in problems. Now, this is very clearly a directed graph. We're adding an edge from every cell to another cell dictated by the array value. So we have a directed graph and we're asking for a single path. But yeah, but the intended solution doesn't actually use graphs. You can basically just like simulate taking the path and then until you get to the end. And again, every like portal moves you forward, so it's going to finish in O of n, and n is 3 times 10 to the 4th, so it'll be fast enough. Okay, now for chat. What's the expected difficulty? Okay, compared to the last one, this one's a lot easier. Like the average problem, the median problem is around like 1600 or so. The hardest problem is a 2600, but everything else is less than or equal to 2100. So it's much easier than the previous one, for sure. What if the last element is 2? Well, that would take it outside the map, but the point of this constraint is that can't happen. So this is index 7, meaning that we have the constraint that 1 is less than or equal to A7, which is less than or equal to 1. So that's what this sort of weird constraint is for. It just means that no portal will ever be large enough to take us outside of the map. Right, so let's see, what else? We can create a Boolean visit array. Yeah, that's one way to do it also. Or what about the case where the starting and ending vertices can vary? Well, there's sort of nothing special about 1, right? I mean, we're just saying like, we're gonna start somewhere and we're gonna go along this path until we either reach the end or we reach t. Right? So like, it doesn't really matter where we start. The point is we're gonna start somewhere and we're going to just go along because we only have one place to go at each point. So if we ever reach t, then we're successful. Otherwise, there's no possible way to do it because we literally looked at every possibility because there's only one possibility. If we're required to print the path, well, in this case, you can simply like, when you visit a vertex, you can sort of just append it to the path. So for example, like here, say we start at vertex 1. So vertex 1 is in our path. Then we go to vertex 2. So now vertex 2 is in. Then we go to vertex 4. Now vertex 4 is in. In this case, we would reach t and we'd be done. So this would be our path. But if we want to go further, then we go to vertex 6, 8, etc. In a general directed graph, what you can do is you can store sort of like the parent. Like for example, say I did this. You can store here that the parent of this edge was 4. That is, to get here, I came from 4. And then to get here, I came from 2. And then to get here, I came from 1. And that way, to trace the path sort of backwards, you can trace the edges you took backwards. And you can figure out we came from 4 here, so 4 must be the last part of this path. Then we came from 2, so 2 must be the second last. Then we came from 1, so 1 must be the beginning. In other algorithms, such as shortest path algorithms, which I will deal with later, that's sort of a common idea. You store only the first place that you came from, and then you can trace the path backwards. Yeah, so this one is, the previous one was about dynamic programming optimizations, so it was much harder. Like the third last problem was 2700, this was 2800, and this was 2900, and the rest of them are also pretty hard in between. It was just a harder topic in general. Also, someone asked if you can solve this with DP, and the answer is yes. But I've already done 3 DP streams, so I don't want to talk about it anymore. But yes, you can do it with DP. It is possible. Okay, anyway. So the point is implementation. So we're just going to straight up just do it. Again, we're going to start at 1 and then just go along the vertices until either we reach T or we hit the end. Okay. Now, one sort of annoying part is that the n doesn't have a value, but T can possibly be n. So if this is the case, then we don't necessarily want to stop at n, but first we want to check, like, can T be 1? Okay, now. So first we want to check, like, if T is n and we're at n, then it's still possible, otherwise not. So the implementation might be a bit, it could be possibly caseworky. Although, something else to notice is that also because of this constraint, and because every AI is greater than 1, we're always going to be able to reach n. Just because, like, at every point that isn't n, we can keep going right. So eventually we have to reach n. So no matter what, we're going to be able to reach n. So if T equals n, we can print that as a special case. But there's also another sort of smoother way to handle it that doesn't even worry about that. So let me get rid of this old code that I wrote for virtual. Alright, so we're going to read in the values. We have n and T. Why is my caps lock on? And then we're going to read in the values. Note that we don't have n values, we have n minus 1. So, let's see. So we're going to keep the current vertex. And right now it's 0. And only because I'm going to use 0 indexing. It doesn't really... Actually, wait. It might just be easier to make this be 1. So we make this 1, then... So we check... How'd this work, actually? Yeah, so first we move forward. We know T can't be 1 because it's greater than or equal to 2, so we don't have to check that. So first, we move forward. Cur equals cur plus a cur, because that's the portal we go to. We're going to go from cell I to AI. Except it also has to be minus 1 because I'm doing 0 indexing with the array, but 1 indexing with this, which is a bit confusing, but whatever. So now, if we're at T, then we're done. Otherwise, we continue. So while cur is less than n. Yeah. So that's it, because like it's just this. We're just simulating moving along until we reach the end. And if we reach the end, then we know we can't go any further. But until then, we're going to check every path. We're going to check every point that is visited by our path. Okay. What have I missed? Galen is the enemy of second thread. Yes and no. I mean, I don't think we hate each other, but it's sort of more the fans are stirring things up than us ourselves. Come on, don't bring politics into this. This is a programming stream. We don't have to fight or anything. Because in my experience, whenever anyone brings up politics, it always ends up becoming a fight or something. So I don't think that's worth it. Let's just avoid that. You can always reach n. Is that guaranteed? Well, yes, but like not explicitly. Because part of the idea is that we can never go outside the map. So every vertex will keep us at a vertex between itself and n, and every value is at least 1. So at every point we can always move right. So it's sort of like a consequence of the way the input works, so we can always reach n. But that doesn't even really matter because we're going to check it anyway. So that will do it then. Print yes. And print no. Looks good. Although I'm kind of scared because I have like a streak of failing on system tests. I'm not exactly sure why. It's just sort of something that's happened. I guess this will take a while. What? Alright, well, while this is running, I can show you what I'm talking about. That I have like a streak of just failing on system tests, like consistently. Because what happened is I took this virtual of the previous div 2. Are you guys ready for this? I got 2 separate wrong answers, both on test 21, both of which were on system tests. Which is sort of unfortunate, because if that didn't happen, I would have been like 4th, but I guess that's how it goes sometimes. And then later I did a virtual that same day, and then I also failed system tests on a different problem. So that's just sort of been happening. Yeah, also I've solved this one, but I'm going to do it again just because of the stream. So yeah, I've already gone over the code. That's basically it. You can see this, right? My submission should be public, I would believe. I would hope. Oh yeah, the messages. I forgot to check those beforehand, but I've been a bit behind in responding to messages, admittedly. I will get to that later. Yeah, this is between problems. I am trying to do that more, not be so distracted by chat. But this is between problems, so I haven't started B yet. Let's see. I can get started in learning recursion. Not entirely sure. Recursion's sort of like a weird concept to tackle, but I suppose the easiest thing to do would be to just start with easy problems, like the most basic ones, like Fibonacci and stuff like that, and then afterwards sort of understand the way trees work and stuff. I don't know. That's sort of, I'm not exactly sure how to answer that. Recursion is a hard topic to like get into your head at first. Like definitely learn recursion and trees separately. And then you can, once you know recursion, you can figure out how you'd be able to apply that to solve tree problems. But you should learn them separately because they're sort of separate theory. How long is this session going to be? I plan to finish the mashup. I don't know how long that's going to take, but we'll find out. Is there any way you can improve code cleanness? No. Besides practice, no. You just sort of like gotta do it. Like force yourself to not do annoying things that will mess up your code. Like for my YouTube, I actually started getting rid of most of my template. I kept LO for long because I can't live without that, but everything else is not that necessary. So yeah, now we're on B. So let's do this. That should work. Now pin that. Right. So we have a problem called rumor. Let me get rid of this now. Don't need that anymore. Okay. Volvo promised himself that he would never play computer games, but recently Firestorm, a well-known game developing company, published their newest game, World of Farcraft, and it became really popular. Of course, Volvo started playing it, so he's addicted. or something. Yeah. Now he tries to solve a quest. The task is to come to a settlement named Overcity. This is just full of parodies. Overcity and spread a rumor in it. Vova knows that there are end characters in Overcity. Some characters are friends to each other, and they share information they got. Also, Vova knows that he can bribe each character so he or she starts spreading the rumor. The ith character wants CI gold in exchange for spreading the rumor. When a character hears the rumor, he tells it to all his friends, and they start spreading the rumor to their friends, and so on. So that's sort of interesting. And the quest is finished when all end characters know the rumor. What is the minimum number of gold he needs to spend to finish the quest? Okay, wait. I've missed some stuff in chat. Yeah, it should be useful to beginners. I'm trying to like make it work for all levels. So the later problems will be better for people who are more well versed in graphs, and the beginning is just sort of introduction to everything. Variants of Dijkstra problems. Well, I have one. I planned to have two, but like I sort of couldn't do it because it was too much of a mess in Polygon. So I have this. I did prepare this problem G. So it is sort of a Dijkstra variant, and then this is also one, although it's much harder, so it'll be more of a challenge. Although I don't think I have any more, unfortunately. Yeah, I'm not sure where to find that. I think you can just like any sort of hard shortest path problem will let you do that. Like for example, if you add a tag of shortest paths and then you have it like be a high difficulty, then it should be better. Or it should be like something of that sense. Did I get accepted to college? No, not yet. Or I don't know yet. Okay, I guess, yeah, I don't know. If you already did G, I mean, the next thing to try would be K. It's really hard, but it's sort of really cool also. Okay, anyway, I'm gonna get back to the problem now. So, basically the way this works is, look, it's a graphs mashup. We're working with graphs here, obviously. So, look, we have n numbers. So let's consider these people as vertices. We're working with a graph. We want to start seeing graphs in certain problems. So each person has a value, 2, 5, 5, 3, 4, 8. Each person has like a cost or something. So now we have m connections between characters, or rather they're friends, but they're connected. So we have a connection between vertex 1 and vertex 4, and we have a connection between vertex 4 and vertex 5. And what's going to happen is when what does the problem say? When someone starts spreading the rumor, or when we tell someone the rumor, what happens is that they're going to tell it to all their friends, and then, or let me start here. So if we start spreading the rumor, they're going to tell it to all their friends, and then those friends are going to start telling it to all their friends. And if this guy had more friends, then he would keep doing it, and so on. And he might even tell multiple friends if there are multiple friends. So a separate way of thinking about this is, like, while we have some vertex that's not visited yet in the current, like, that's interesting. It's like a connected component, right? Then we're going to keep going until we fill in that whole component. So basically, because every friend will spread it to every other friend that they're connected with, like, every node that's connected, like by this definition, where there's a path between the two nodes, will be eventually considered, or will be eventually get the rumor just from sending the rumor to this friend. Because this person will tell it to all their friends, and then these friends will in turn tell it to all their friends, and sort of every vertex that has a path to this will be told by some previous friend, because some previous friend will be told by some previous friend, and eventually like sort of chain back to the original vertex. But yeah, otherwise, like, that's just sort of how it works. Yeah, okay, I don't think that's the best explanation, but I mean, it sort of works. Like, just intuitively that everything in the same connected component will eventually be reached by this vertex because it's going to like it's going to look at everything that's ever connected by an edge to this one because all the friends are going to like tell it to all their friends and so on. But if we look at this vertex, this guy has no friends, which is unfortunate, but it means that there's no one that he'll tell the rumor to. And for example, this guy as well. So they'll sort of be isolated. But if we tell the rumor to this guy, then he'll tell it to all these people. So really for each component, we only need to tell the rumor to one person. And which person do we need to tell it to? Well, the best thing to do would be to simply pick the smallest one. Because no matter what, like, it doesn't matter which one you pick, it just means that like everything is going to be like you need to pick one value for each component and not more than one because that'll be an extra cost. And so because you can pick any value in the component to make it work, and you want to minimize the total cost, the best thing to do would be to simply minimize the cost for each individual component. And the way to do that is just to look at each component and say which one has the smallest cost. So really what we're going to do is we're going to first find these components and actually draw correctly and not cut off the numbers. So we have 3 components, and then each component is sort of independent. We need to tell the rumor to one person this component, so we look for the minimum cost of this component and we'll be done. Okay, that's the explanation. Now I can read chat again, and then we'll go to implementation. Which one should be done if you're around 1700? I think a good starting point for like medium people would be A to E are sort of easier. So this F is where it starts to get harder, as you can see it drop in difficulty. So this may be a good point to start for 1700. And then G to J are even harder, and then K is insanely hard. So yeah. Yep, summation minimum value across all connected components. Yeah, that's basically it. Code chef or code forces? Personally, I would say both, because like, why not? But if you're really constrained for time, code forces has sort of more quality things and a more diverse problem set, and also like a huge problem set, so it's easier. You're gonna have more resources on code forces, so I would think it's better. Can you solve by using path compression? I'm not sure what that means. If you mean something like DSU, then yes, but I'm not sure. Did someone swear in Hindi and I didn't even realize it? I don't know words. That's true. After you learn recursion, what can you use to learn binary tree? Stuff like that. I'm not exactly sure how to teach those because I don't know the most about them, but I'm sure there are other things online that can help you learn those things. I wouldn't know myself. Yeah, alright, thanks for timing them out then. Yeah, I would not even notice. So, DSU on connected component? Yes, you can do that too. It works. I mean, whichever you want. Although, okay. So because it's an introductory like thing, and I just dropped my pen on the floor, we're going to first teach how to mark connected components, because I sort of just glossed over implementation in the beginning. Right, so say we have some sort of component that looks like this, for example. I'm just going to draw some edges between them. So we have like a triangle, like so. Basically, we want every vertex in this component to be visited somehow, because they're all connected to each other. And again, we're assuming an undirected graph, so there are no arrows. Every edge goes both ways. It means I can go from here to here and from here to here. Yeah. So every pair of vertices must be connected. So that means if I pick any vertex, it has to be connected to all the other ones. So I should be able to start from any vertex and then look at all the things that this vertex is connected to, and then everything will be in this component, right? So the algorithm for this is I pick any arbitrary vertex. For example, let's say this one. Then I'm going to look at everything it's connected to, and then everything that's connected to will be in the same component. Now, why am I allowed to only look at one vertex? So for example, say this can reach everything. But for example, we could have some contradiction by saying two things that this can reach can't reach each other. Like for example, assume these two weren't connected. So assume this algorithm is not correct. And therefore that when we start from this vertex, even if we can reach all these vertices, somehow some of these vertices can't reach each other. So assume the algorithm is incorrect. Let's prove it's not incorrect. Right? Well, if we have these hypothetical vertices that this vertex can reach, but they can't reach each other, because this graph is undirected, this being able to reach this also means that this can reach this because we can just take the reverse path. And similarly for the other one. So for these two hypothetical vertices, both of these can reach the starting vertex. By definition. Like, that's what we just did. We just figured that out, right? So now we have a path between these two vertices. We go from here to the starting vertex, and then from the starting vertex to here. So therefore, there cannot exist two vertices that are both connected to here but aren't connected to each other, because you can just go here and then take that path, and then like that would be how it works. So basically, I'm just proving that it's enough to start from any vertex and look at all the vertices that this is connected to. Now, how do we do that? Well, the main idea is we don't want it to be exponential. So to avoid that, we're only going to visit every vertex once, because say we like, for example, go here and then go here, and then now we visited this vertex. So now what that means is that like we're done with this vertex. At this point now we're going to look at everything this is connected to and then continue on. But if we ever visit this vertex again, like we've already looked at this vertex and at all of its neighbors, because that's what we did the first time we visited it. So there's never a reason to visit a vertex multiple times. So what we're going to do is we're going to start from some vertex. Then we're going to look at all the vertices that are directly connected, all the neighbors of this vertex. And two vertices are neighbors if there's a direct edge between them. Not directed, direct. So then we mark all these so we mark the initial vertex as visited. Then we mark all these vertices as visited. And so now, actually no, we mark all these vertices as sort of pending, like we're waiting to visit them. So now we're going to look at the pending vertices. So this is the first pending one, so we can say we look at this. Well, this vertex only has one neighbor, and that neighbor's already been visited, so we have nowhere else to go from this one. So we're done. And now these other two are pending, so we're going to look at both of them. Now let's look at this one. So this has two neighbors. This one is already pending, so there's no reason to look at it already. But this one is new, so this is sort of a new vertex that we can reach. Even though it's not directly connected to this one, there's a path between this one and this one, which we just found by going this way. So now, sort of, this vertex is done, and now both of these are pending, and then eventually we would visit both of them. So then everything in the component will eventually have been visited, and everything that's not in the component won't even be relevant. Like, we will never look at it, because there's no way we can get from here to here using an edge. So this sort of pending thing is the way BFS works, which is breadth first search. And there's also a different one called depth first search, which is sort of a different version of it. I think depth first search is a lot easier to write, but it's also it has different disadvantages, which I will go over later. Also, this is abbreviated as BFS and DFS. So let's look at DFS now. The way DFS works is we go here, and we're going to do the same thing. We're going to visit all these neighbors eventually. But the idea is not yet. So first here, we're going to look at all these vertices. Then we look at the first neighbor, and then we go to that neighbor. And then eventually, like sort of in a stackish manner, we're gonna return back to here, but only after we finish exploring this vertex. So we go here, we look at this vertex, we look at all its neighbors, it has no neighbors. So we mark this as visited, and we're done. So now we look at more of these neighbors. We go here. Now we look at this vertex's neighbors. So we can go here, and we can go here. And all this time, somehow we're keeping track of the vertices we visited. Like for example, I can stick these in a list, and then we know that this list has all the vertices in this component. But yeah, and then once we're done, now this vertex is visited. And then now we have no more neighbors to check because everything else has been visited, so we go here. Now, we would have checked this neighbor initially, but because it's already been visited, there's no reason to do so. So we just get that all vertices have been visited eventually. That's the basic underlying idea between these searches. And because we're visiting all neighbors of all neighbors of all neighbors of all neighbors, etc. of the starting node, like it's going to reach everything in the component eventually. So that being said, this actually, implementation-wise, is not so terrible. I'm going to start writing the code and then possibly start explaining it as we go. So let's see, we're going to read in the values and then the edges, and they're going to read in the number of nodes and the edges. Also, by the way, vertices are interchangeable with nodes, so if I call it either, they're both the same. So we're reading the cost. Now we have edges. And the way to represent this in code is to simply create a vector of adjacencies, or a list of adjacencies. So the way this will work is, let me get rid of some of these scribbles. Say this is vertex 1, this is vertex 2, this is vertex 3, this is vertex 4, and this is vertex 5. For each vertex, we're going to simply store the list of things that it's connected to. So 1 would be connected to 2 and 4. 2 would be connected to 1. 3 would be connected to 1, 4, and 5. 4 would be connected to 1, 3, and 5. And 5 would be connected to 3 and 4. And that way we just know the neighbors of everything. So we're going to do that now. We're going to say we're connecting vertices u and v. Because we zero index, we have to decrement them. Then we know u is a neighbor of v, so we add v to u's adjacency list, and then we do the same thing for v because we know u is a neighbor of v, or v is a neighbor of u, etc. Yeah. So then we also need this visit array to make sure that we don't visit any node twice. And also, if we visit some node in some previous component, like for example, we start at 1, then we visit all of these. So then now we're looking at 2, but we've already visited it, so we know it's some component we know it's inside some component we've already looked at. So we only need to look for components with vertices that we haven't visited yet. So the idea would be, now we go through all vertices. If this vertex has not been visited, then let's do DFS. So the reason I have this return a value is because this is simply going to return the minimum value in this component. So there are two cases. The minimum comes from this vertex itself, the one we're currently at. So then we start the minimum off at the current cost. then we also say that this vertex has been visited. So then now we go through, we look at all of the neighbors. So for each neighbor of this vertex, we're going to go into it. So now the other case is that the minimum comes from some vertex in the neighbors, or some vertex that we would visit from a neighbor. So in that case, we would do that. Or rather, we should say if we've not visited this node before, because if we have, then it's sort of if we've not visited this node before, because if we have, then there's no point to repeat again. Otherwise, we look at everything. So now return the minimum value in this component. Return min. So that does it basically. Or not. Oh wait, yeah. Sorry. For each edge connected to V, not for each V, which wouldn't even make sense. Then we look at the neighbors. Yeah, I'm gonna do BFS in the next one. Don't worry. I'll have everything covered. Anyway, this has no edges, so everything is by itself. So the answer must be the sum of values. And here, we should get 15. Yep. So that basically does it. 100,000. Make sure we're using longs, etc. Yeah, okay. So from where should you practice? Generally, the best way to do that is to like go to the problem set or something, and then find just some difficulty that's hard for you. The rule of thumb I like to use is that if it takes less than like 30 minutes or something, it's too easy. But you can adjust that if you want, but you just want to find some difficulty that's hard for you. So you can go to the problem set and just start solving random things. Make hard mashup? Well, this is sort of hard. I mean, look, these later ones like go up to 2100. So if that's hard for you, then that's possible. And this last one is also going to be very hard, for sure. So maybe it's relative to difficulty, but I mean, it should be somewhat challenging at least. Let's see. C is more DSUable. Yes, I will do DSU later. I'll try and cover as much as possible. The stream we save public. Yes, after the stream, it'll be available on YouTube. So it should be good. Yeah, BFS, I will cover that. What is the max recursive call allowed in C++? Depends on the compiler. Sometimes you get restrictions, and sometimes you get a stack overflow. It depends on the memory you use. I think like by default or something, the maximum is like 9,490 something. I remember this being the number I saw, but what you can do to avoid that is you can sort of like you can set the stack size in the compiler flags so that it will give you more things. Like for example, you can search this up and then or like G++, whichever compiler you use, and you can have it to give you more stack size, and then yeah, like something here, and then it will let you increase it. But actually it is pretty small. Like I don't think it would work for most problems otherwise. But Codeforces also gives you a massive stack size. Like the stack size is about the size of the memory. So in Codeforces, you won't have to worry much about it. Okay. Why do I use long everywhere? It's just to be safe. I use G++64, so using longs in most cases is actually faster than ints using this compiler. But I just do it to like avoid overflow, basically. Like that's all it is. It's just to avoid overflow. Do I like Danilo? I don't know who that is, so I don't know. Oh, updating the sub count. Shoot, I did forget to do that. Right. Okay, that is something I forgot to do. That's true. So as always, I stick my subscriber count in my template. And then the eventual goal is when I get to 9 million, if I ever get to 9 million subscribers, that this template will cause me a memory limit exceeded verdict. So if you want to contribute to that, you know what you need to do. Yeah. Hashtag get me MLE. Okay. Alright, let me get rid of this mess. Alright, now this is a new problem, so I'm going to update the everything. This current problem is C. Right, so in some social network, there are n users communicating with each other. N users in m groups of friends. So that's interesting. Let's analyze the process of distributing some news between users. Initially, some user receives the news from some source. Then he or she sends the news to his or her friends. Choose their friends if there is at least one group, such that both of them belong to this group. Friends continue sending the news to their friends, and so on. The process ends when there is no pair of friends, such that one of them knows the news and another one doesn't know. For each user X, you have to determine what is the number of users that will know the news if initially only user X starts distributing it. So we sort of have a graph, but it's sort of weird at the same time. Okay, I can read chat again. The stream be saved public. Yes, it will. After the stream, it will be as an archive on my YouTube. Like, for example, if you go to my channel, you can see that all the rest of them are here. Like, for example, all the previous streams. And also, I have a playlist of all of them, so yeah, you can find that there too. 10K is nearly here. Yes, I do remember. I know what's happening at 10K. When do I usually wake up? For school, it's like 8 or, yeah, usually 8-ish. For contests a bit later, usually 8:30. Because they all start at like 9 a.m. or something, or contests are always 9:35 usually, except for weird timings. Whoa. Yeah, okay. So, oh, jaw hurts already. This is not good. Okay. So how does this problem work? We have a lot of users. So let's say we have 7 people. Drawing them in a circle, so I'll label them 2. So 1, 2, 3, 4, 5, 6, 7. We have a list of people, or we have a list of groups. So we have one group that's 2, 5, and 4. Meaning that... How does this work? Right, yeah. So it means that 2 is friends with 5, 5 is friends with 4, and 2 is friends with 4. It means every person in this group is friends with everyone else. And similarly, we have another group, 1 and 2, which means 1 is friends with 2. This has 0 for some reason. I don't know why they would do that, but we have a group with 1, which means nothing. 1 is friends with itself. And we have 6 and 7, which means 6 is friends with 7. So let's see. We have that. So how do we do this, right? Well, being in the same group as someone means that we have an edge between them, because we can consider friendships to be edges. The problem is, like, say we have a group of size 5 times 10 to the 5th. Then if we create an edge between every person and every other person in that group, we're going to have, like, what is it, like 10 to the 11th? We're going to have around 10 to the 11th people. Yeah. So we're going to have around 10 to the 11th edges to create, which is insane. There's no way we can do that. That's too large. We can support maybe like 10 to the 8th to 10 to the 9th, somewhere in that range. Especially in memory, actually. We have a memory limit. So we can have at most like 2.5 times 10 to the 8th edges, just because of memory. Yeah, so we can't do that. But like we also don't need to, right? So say we have like a group of size 5. What we want is, we don't need all of these guys to be friends. Like say I draw all these edges and etc., right? I can draw all of them. But all we need is that this whole group has to be connected somehow. That I should be able to reach 5 from 1 using only this group, because this group is friends. But say I add the edge between 1 and 2, and then say I add the edge between 1 and 3. Now if I want to add the edge between, I add the edge between 1 and 2 and then 2 to 3. Now if I add the edge between 2 to 3, it's sort of redundant, right? Because we've already connected, or if I add the edge between 1 and 3, God, my numbers are off. It's sort of redundant to do this because we've already connected them using this. So there's no reason to add another edge that connects them when they're already connected. So right? So similarly, when we stick on the next one, we know these two are connected. When we stick on the next one, there's no reason to make this guy friends with everyone, because we already know that these 3 can reach each other. And so all we're doing is connecting it to this already existing component. So we only need to add an edge between 3 and 4. Or really, we can also just add an edge between 1 and everything. That would work too. Although for implementation's sake, I'm going to add these edges. And this is enough. Now this whole group is connected, and we only added O of, what is it, like size of group edges. And so the sum of the sizes is n, or sum of the sizes is m. So that's enough. We have O of m edges at most. That's what it is, right? O of m. Oh, yeah, 5 times 10 to the 5th. Yeah, okay. Well, it's not m, but it's like, it's bounded. That's the point. We don't have too many edges. It's linear edges. Cool. Yeah. So that's how we handle a group. And then from there, we're just interested in how many. So for example, say we do add these edges. So let me actually construct this graph out now. So we have 2 to 5, then 5 to 4, then we have 1 to 2, then we have 6 to 7, right? Now we're interested in, for each person, when we, we give the news, so it's news again. When we give the news to this person, how many other people will it reach? Or how many people in total, right? So that's just the size of the component. It's the same thing as before. How many people is how many people are reachable from here, which is the size of this component. So really, once we add these edges, we just find connected components, and for each one, we print its component size. That would be it. Okay, I'm gonna add someone as a friend. Okay, sure. Give me their handle. If they're that dedicated, sure. Give me their handle. Am I gonna cover CSDS? Not here. Potentially later. But like, there are also other videos on CSDS, like William Lin did like a 12-hour speed run or something. That's sort of interesting to check out. I was watching my topic stream for DP the other day and I had trouble pinning a message. Yes, I did, but it wasn't my fault. Like, I straight up didn't have the option. I knew it was possible because someone said it, but I didn't have the option until like right after that stream when they told me now I have this option. So it wasn't my fault. It was just that they didn't give it to me yet. I have to defend myself for that because, you know, during that time when I was struggling to pin the message, that was when I had peak viewership. Like, that was the only time I had over 180 viewers. Everywhere else, when I was doing normal stream things and not struggling to set things up, I had fewer viewers. So maybe a good thing to do is just to like start having audio problems out of nowhere, and then that maybe that'll promote my stream more. It's an interesting strategy to do things like that. Just make a fool out of myself on purpose. That would be the idea. Did I not pin the right thing? What? Did I forget to pin this? Seriously? See, I'm still having trouble pinning messages. There we go. Perfect. Doing it by itself. Anyway, yeah, we're on C right now. So, alright, so expect some sporadic stream problems sprinkled throughout so that people can stay. No, it's not 9,000 subscribers. I don't know when it happened. I think I like had to do a stream or something, and then I don't know what the criterion is, but I got it a long time ago. Like I got it between the first and the second topic stream. I don't remember when that was though. Okay, anyway, so now we're going to, instead of using DFS, now we're going to implement BFS, which is breadth first search. And the way breadth first search works is that we're going to start here, and then we're going to put all the neighbors in sort of like a queue. And then we're going to visit the neighbors in the order of this queue, and then we visit this neighbor, and then we put this neighbor into the queue, and then we visit that. So the first thing we do, so the order that we sort of do things in is we visit the initial node first. Then we visit everything that's distance 1 away from this. That's sort of the way the queue will do it. And then we visit everything that's distance 2 away, and then everything that's distance 3 and 4 and etc. So that's kind of cool because it means that BFS will actually find us the shortest paths from some vertex to some other vertex. It will find us the shortest distance from every vertex to this one using BFS. But this only works if all of the edges weights, if all of the graphs weights are the same. If we have, for example, say this is like length 2 and length 5 and length 3, it'll work for this because it's a tree, but don't worry about what that is. But everything else, like BFS can only be used to find shortest paths if all the edges either don't have a weight or they all have the same weight. There are some variants on BFS that will work also for some other special cases, but there's a generic shortest path algorithm that we'll go over later. But don't really worry about that for now. It's not really necessary. The point is, the main difference between DFS and BFS is that DFS uses a stack. So we'll go here and then go here and then immediately visit this vertex instead of looking at the neighbors. And then once it's done, it will go back up the stack and then immediately visit this one and then immediately visit this one. And if this had some other neighbor, it would ignore it until later. Whereas BFS uses a queue. So it puts all the neighbors in line, and then it starts visiting them in that order, and then it puts all of the neighbors of those neighbors in line, and it just continues. That's the difference. Like, basically the only difference between BFS and DFS is that BFS, or like implementation-wise, is that you would do DFS with a stack and BFS with a queue. So let's get started. Let's read in the values. Then we have m lines. Each is a group of friends. So we're once again going to use the representation of a bunch of edges, where we have 5 times 10 to the 5th for no good particular reason to have such high constraints, but whatever. So now we're going to, for each group of friends, LOK, K is the size of the group. So we're just going to put this in a vector because why not? Then for j equals 0, j is less than k, j plus plus. Read in the values, so just c into vj. Then for every pair of adjacent nodes in this list, we're going to add an edge between them. So for example, we're going to add an edge between v0 to v1 and v1 to v2 and etc. So we're going to add an edge between v0 and v1. So edges vi dot push back vi plus 1. We do the same thing, but because it's undirected, we have to add edges both ways. And this will make this whole friend group connected without having to explicitly add all the edges. So this sort of thing, this sort of trick is used all the time. Like, when we want to connect some group of vertices, we don't do it explicitly, because we don't need to add all the edges. We just need to add some edges, sort of like in a line, so that we don't have to connect everything. That would be the basic idea. We're currently at C, finishing things up. I think the pinned message should show you that, but maybe it doesn't show up on some browsers. Okay, right? So now we're going to do BFS. So we also just realized, like, did I just not do that? Okay, I think I might have gotten lucky here, but generally what you would want to do is you would want to initialize all visited to 0 using like a memset or something, otherwise it's dangerous. I'm not exactly sure how that... I don't actually know how that worked. Oh, right, yes, that's true. This should be VJ, that's true, my bad. Otherwise that would be a weird bug to try and fix. Thank you for noticing that. I'm not actually sure how that worked. I think it has something to do with the way global arrays are initialized, but that's sort of lucky that that worked out for me. Yeah, like I think global arrays should initialize to 0, and then local arrays are weird, but global arrays should be fine. So I must have gotten lucky there. Yeah, lucky that like I didn't do it locally. Okay, so this isn't necessary, but I'm gonna do it anyways for the point of... Okay, yeah, I don't know much about the language, to be honest, but if it's always 0, sure, that works. So now we do BFS. Alright, fine, I guess I don't need this, since it always initializes to 0. Oh wait, also we want to... This is one index, so we want to not have that exist. Alright, so once again, we're doing the same thing. We're only in a new component if we haven't already visited this. So otherwise, what we're going to do now is we're going to do BFS. And the way this works is that, once again, we can start at any arbitrary node and simply go out and look at every other node that's adjacent to this. And the way we do this, once again, is we use a queue. So we're going to start by pushing simply our initial node into the queue. We know that I is going to be part of our new component because I has not been visited yet, so we'll start with that. Then the idea is, while we still have stuff in the queue, then we keep going. Because if we don't have anything in the queue, it means we've looked at everything already. Hang on, I'll get to questions after this, because some people have been complaining about that. And I understand the complaining, so I'm not ragging on people, I'm just saying. It is sort of annoying to keep like going between chat all the time. So, and yet I'm doing it anyway. So we're gonna look at the beginning of the queue. So queue.front, and then if we've already visited it, then continue. All right, first we want to also pop the beginning of the queue. If we already visited X, then continue, because we want to continue this loop. If we do break, it means we'll just stop the BFS altogether. I made this mistake before. Don't be like me. So then we say that this this node is now visited because we just visited it. Now, for every possible other vertex, for every node that's adjacent to this current one, if not visited Y, I'm sort of doing double checking, but that's fine. It'll save us some memory. Like you can engineer it so you don't necessarily have to check visited both times, but it doesn't matter at all. Oh yeah, parens, true. And otherwise, now this is a neighbor, so we push it into the queue. And also, we're going to Yeah, I made a typo. We're also going to look at this. We're going to store all the nodes in this component because we need to like for each component we need to set its answer equal to its size. So we need to have the actual nodes in every component. And we can't do it while we're doing the BFS because we need the final size, and we don't know the final size until the BFS is done. So for convenience, I'm just storing everything in a vector. So this is the full component. Now that's it. We just look at all the neighbors. Then for LLX component, for each thing in the component, A is going to be the answer, and then its answer is the size of the component. And that's it. Right? That's the idea. And we get the right answer. If you're confused, it may help to check out the beginning of the stream. I sort of do... The point of this is to be an introduction to the way graphs work. So it's like... If it's confusing, I do give definitions for everything and sort of like try to introduce them. I'm not sure how good of a job I did because I didn't feel that great, but who knows. Anyway, this is going to be O of n because BFS visits every node exactly once. Or O of n plus m. Just the number of nodes plus the number of edges. .358 milliseconds. Okay, and just to illustrate my point, I'm going to do the exact same thing, but replace it with a stack. Right? Now this is DFS now instead of BFS. Because we're using a stack instead of a queue. Right? I'm not going to rename this. It's just going to be a stack called queue, which makes no sense, but yeah, that's it. All right? So this is like iterative DFS. It's simpler to do it recursively, which is what I did in the last problem because it's less code. But you can also do it iteratively. You can like have a stack and do this and avoid any sort of recursion. And people often do this in Python, actually, I think. Because that's just how it has to be done. Actually, it's not exactly the same as DFS. Actually, yeah, I'm kind of wrong. It's not exactly the same as DFS, but it's like very similar. I think it might be. I think it would be. It should be the same as DFS, but I'm not going to make any claims. I'm just saying it's similar. It's a stack instead of a queue. But I think it is the same as recursive DFS, like the same order of visiting the vertices. I don't know. It's just because like would it be? Yeah, I guess it would be. Yeah, yeah, that's true. I don't know why it wouldn't be. Because we're still like, I mean, the thing that could be concerning is that we push all neighbors into the stack before we move on to a new vertex. Like we don't, unlike normal DFS, we don't interrupt. Like with recursive DFS, we interrupt visiting a current vertex to go into the new one. But in this, we push all the neighbors into the stack before we interrupt it. But it should still be the same order, just a different way of handling it. So I think it should be the same. That's what I'm thinking. Okay, what am I covering? All right, so a general overview of what's happening. This is basic, like, what is a graph? This is connected components. This is bipartiteness, which we're about to find out what that is. This is using DSU. This is working with directed acyclic graphs. This is dijkstra on a special graph. This is a spanning tree. This is also a spanning tree problem. This is interactive, and this is hard. I'll leave it at that. Can you briefly explain memset if it's not that hard? I can try. I mean, okay. Basically, the way memset works is like, look, so, yeah, I mean, memory is just like a long list of things, right? Or maybe not, but, you know what? Actually, no, I can't explain memset. I don't want to give you guys the wrong idea because I don't really know how it works, so I trust that some reference can explain it in a better way than I do. So never mind. It's not a good idea for me to try to explain that, because I'm gonna like say something wrong and then it's just gonna mislead you. I'll say, yeah, what's up, Denjo? What's up, everyone? Everyone is here. Surprise, the high viewership usually doesn't last this long, so that's kind of cool. Right, now we have D, so we're gonna do that. Yeah, sorry, I don't want to say something wrong and then mislead you and confuse you and everything. But, look, the most important part of memset is that, like, say you have an int, right? So it has 32. I'll give you like the practical side of memset. So you have an int. So an int is 32 bits. So we're gonna should we pretend an int is 24 bits because I don't have enough space. All right, that should be fine. Yeah. So we have an int, and we're gonna break them into groups of 8 bits because the way memset works is that it only does it per character, and a character is 8 bits. So if you want to memset to something like 2 to the 8th, like for example, this would be 1 and then 8 zeros. That's not possible because the only thing you can use is a character, which is at most 8 bits. So like, for example, if I wanted to memset everything to 1, what it would actually do is for every 8 bits, it would memset it to 1, but for every group of 8 bits. So it would fill this group of 8 bits in with 1, but it'll also do it for the other group. So put that here, and then put that here, and then put that here. So you get this very unexpected behavior when you use memset for certain numbers, because like this is going to be 2 to the 24th plus 2 to the 16th plus 2 to the 8th plus 2 to the 1, or 2 to the 0, right? So you're going to get some huge number and not expect it, because that's just how memset works. It's by characters. So my advice is just to not use memset unless it's for 0, unless you want to set values to 0 or -1. And the reason is that -1 just happens to be like all ones, meaning that no matter what you do, any form of memset you do will be all ones. And for 0, it's the same thing, that everything will be 0 anyway, so it doesn't matter how many times you repeat it, it's still all going to be 0. So you can use memset for 0 or -1 safely, and then be careful for all the other values. That's sort of like a practical lesson on memset. But I don't know how it works. Like I don't know how memory works, so I'm not going to try and explain that. I have more viewers when I'm not talking about graphs than when I'm actually talking about graphs. What even is this stream? What am I doing? Should we have gone with bitwise operations? That seems like more popular now. How do we use a mouse? Yeah, I did used to use a mouse. It was just like a lot of things, but it was a lot of practice with mouses. But now I do use a drawing tablet. Yeah, that is a good question. Why are we talking about memset? Oh, it's just because someone asked a question and I went off on a bit of a tangent. But we're gonna get back to graphs now. I was just answering a question. Let me answer a few more questions. For C, you can also use the DSU. Yes, you can use the DSU for anything that involves like merging components. So you can use the DSU for B and C and E and like other ones. I will cover DSU here, so don't worry about that. But if DSU is getting TLE, it's most likely the implementation and something's wrong with it because it should not get TLE. It has a very good constant. So if you're getting TLE with a DSU on something like with reasonably small constraints, I think it should be a problem with implementation. Because DSU is quite fast for its complexity. It's one of the best n-log n's you can ask for, or also like even better. Okay, let's actually do the problem now, because I had this pinned for a long time and I like never did it. So recently, 2 people did some research. I'm gonna avoid saying names because I don't want to mess things up, about NP hard problems, and they found the minimum vertex cover problem very interesting. Suppose the graph G is given. A subset A is called a vertex cover of this graph if for every edge there's at least one endpoint of it in this set. So let me describe that visually. I have my pen backwards, so I can't really draw like that. The number of times I've tried to draw by holding my pen backwards is kind of astonishing. So right, we're gonna add some edges. Like so. Right. Okay, that should work. So a vertex cover is basically, we're gonna pick some vertices. We're gonna like circle them or something. We're gonna pick some vertices like so. And then what we want with this vertex cover is that every edge has to be adjacent to at least one circled vertex. That's what it is, right? Yeah. So for every edge, it has to be adjacent to at least one of the circled vertices. So for example, here, this part will be a vertex cover here. Like in this component, only considering this one, this would be a valid vertex cover because this edge is adjacent to this one, this is adjacent to this one, this is adjacent to this one, this is adjacent to both. It's okay if we have both, we just can't have none. So in this graph, we have a problem because this is adjacent to neither, so we need something else in the vertex cover. For example, this. And then every edge is adjacent to at least one circle vertex. That's what a vertex cover is. Now what you want to do is, you want two different vertex covers of this graph. So you want to split the graph into two parts. That is, say we give it like two colors. So I color some things in blue, and then everything else I color it in green. And so that's what I need to do. And then from that, I need to make it so both the blue vertices and the green ones form vertex covers. So like if I only look at the blue vertices, the blue ones have to make a vertex cover. And if I only look at the green vertices, the green ones also have to make a vertex cover independent of the blue ones. So I want to see if that's possible, and if so, print such a coloring. Yeah, disjoint subsets. Okay, so let's look at this a bit more. Consider some edge, right? No, that's very wrong color scheme. What did I do? Okay. Yep. Consider some edge. Just ignore the rest of everything else. Now this edge has to be part of both vertex covers, right? So it means if we have to have a blue vertex cover and we need to have a green vertex cover, right? So this edge has to be part of both of them, meaning it has to be adjacent to at least one blue vertex and has to be adjacent to at least one green vertex. So if both of these are blue or both of these are green, then it means there's nothing we can do. It's not possible for that to be true, because then if both of these edges are the same color, then we're not going to have any of the other color. Or if both of these vertices are the same color, we're not going to have any of the other one. So having an edge means we have this constraint that these two vertices must be of different colors. Now sometimes this isn't possible. For example, say we take this. Now I say this edge means that these two have to have different colors. So this has to be blue. And then this edge means that these two have to be different colors. So this has to be blue. But look at that. This color is forced by this one, and this color is forced by this one. But we also have this edge that says that we need these to be different colors. But that's not possible, because these colors are forced. If we change these colors, then it would violate this constraint or this constraint. So it's not possible to do this. We have a contradiction in our graph. So in certain cases, it is not possible. Right, so the question is now, how do we figure this out? And first of all, is it enough to find such a coloring where every edge just means you have different ones? And I mean, the answer is yes, because like, if we can satisfy the constraints for each edge, and each edge is connected to two vertices of different colors, then like, we just did it for each edge. Like, we made it so each edge is connected to one blue vertex and one green vertex. Like, that's the constraint we had. So if we can find such a coloring that works with all the constraints of these edges, then that's it. Like, by the definition of like the constraints we had for the coloring, it's gonna work. So now we get into a common theme, which is called bipartiteness. And so what is a bipartite graph? Let's explain what this is. It basically means that you can partition it into two sets, like for example here and here, such that, so this is set 1 and this is set 2. It means that there's no edge between any two vertices in set 1, so these edges can't exist, and there's no edges between any two vertices in set 2. The only edges can be between set 1 and set 2. For example, like this, right? So this is the definition of a bipartite graph. So now what? How do we do this? Well, oh, actually, what does this even mean, right? Like, I just gave you a random definition. Why is this relevant? Well, the idea is that with a bipartite graph, say we color all these vertices blue, and then we color all these vertices green. By the definition of bipartite, we have that like there's no edge between any of the blue ones and no edge between any of the green ones. Can you write the definition? Yeah, sure. So bipartite it's sort of hard to write. It's like it means that it can be partitioned into two sets. This is disjoint sets, meaning there's no vertex in both of them. Sets where like there's no edge between any vertex in the same set. So this is like no edge within set 1 or set 2. So every edge that exists must be from one vertex in set 1 and another in set 2. That is, this is equivalent to saying all edges go from 1 to 2. And that's the idea. Yeah. So why is this relevant? Well, again, if a graph is bipartite, we can color it. If a graph is not bipartite, that means there's no way to do this partition. Then we can't color it, because no matter what, even if we try to color things, there's going to be some edge between what we have. So now we get a standard problem, which is checking bipartiteness. And okay, so a graph is not bipartite. Just a bit more insight into the way it works. A graph is not bipartite if it has any cycle of odd length. That's how this works. So we have a cycle of length 3 here. And a cycle is simply a path that starts at some vertex and then goes back to itself. So, yeah, that's... It's sort of not easy to prove, I would guess, but it should be simple to show that any odd cycle makes a graph not bipartite, because like consider this. Now we started some vertex. Now let's just go around the cycle. So like the next vertex must be of a different color. So we'll say we'll color it orange. Then the next vertex must be of a different color. So we'll color it purple. And then the next vertex, oh wait, look at that. They have to be the same color, right? But that's not possible. So any odd cycle makes it not possible. Yeah, and so for any odd cycle, like it's just not going to work out. You can try it for 5 or 7 or 9, but the idea is the second to last vertex before we get back to this one is always going to be forced to be the same color because the color like goes back to purple every 2 vertices. Whereas for even cycles, it's going to work out because we go from purple to orange and then back to purple. So it works. So it shows that it's an odd cycle is having no odd cycles is a necessary condition. I don't know how to prove that it's enough. I don't know how to prove that if you have no odd cycles, it's guaranteed to be bipartite. But anyway, relevant to this problem, this is sort of less important. What is important is that somehow we have to find this coloring. Right? So let's take something new here. Let's take some graph. In fact, let's take this example graph, right? I'll just copy this over. In fact, I'll make this bipartite one too. So we'll have something here, we'll have something here, we'll have something here. Sort of screwed myself here. We have something here, 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 have something here. Perfect. Okay. I think I can also add this edge without having trouble, but whatever. So the main idea is we have only 2 colors. In general, figuring out if we can color a graph in K colors such that there are no like adjacent nodes with the same color is NP something, NP complete or NP hard. I don't remember which, but like the thing is that we only have 2 colors. So say I color this here. Say I pick some node, right? And I'm just going to color it. I'm going to color it blue. If this node is connected to nothing, great. Then we've satisfied it for that component. Also, it should be relatively clear that every component is sort of independent because we don't care about, like this component doesn't care about any of the colors of this one. So every component is independent from the others. But I'm going to color this blue. Now for every other edge, there's only one possible color everything else can be, which means that this node is sort of predetermined by whichever I color this. Then now, for all these other vertices, there's only one color it can be. So it has to be blue. And say I add this edge. Well, we fixed that this was blue. And then we said that this has to be a different color from this one. And that this has to be the same color as this one because it has to be different from this one, which is different from this one. Which is sort of convoluted, but that's the way it works. That when we pick the color of some vertex arbitrarily, it can be either one, it doesn't really matter. The color of every other node in the component is predetermined just from this color because there's only one other color it can be. This doesn't work for K. This doesn't work for having more than 2 colors, but it does work for this one. Because if we have more than 2, there are multiple colors we can make it. But that's the idea. That we've picked the color of some vertex, and then everything adjacent has to be a different color. And then everything adjacent to that has to be a different color. And everything adjacent to that has to be a different color. And that's how we do the coloring. So really it's like we do the same sort of like DFS or BFS, the traversal, except now we sort of have to keep track of the color we're at, and then we alternate it at every point. And if we ever have an edge that forces us to connect between 2 vertices that are already predetermined, and a way to check if a vertex is predetermined is simply to ask, has it been visited yet? If we have an edge between 2 vertices that are predetermined to have the same color, then it's impossible. And otherwise, look at that, we have our coloring. So really we just do like DFS or something, and we keep track of the color and we alternate it every time. That would be kind of how that works. Alright, what am I missing, chat? I think I missed a lot. Difference between a pupil and a GM. Yeah, it is basically just knowledge and experience. And also potentially dedication. I mean, it does take a lot to get read, I would imagine, but actually I would know, but so yeah, dedication is also part of it, like motivation, being into it. Yeah, there's a really hard explanation for why the complexity is inverse sacrament. It's like a huge paper. I think it's like 8 pages or something. I got like 5 lines in and then started getting confused, so I did not read that much. What competition gives you an undirected graph as a prize? Yeah, some of these statements are a bit absurd, but it's still funny. Topic-wise mashup. That is sort of what this is. It's just like it's subtopics of graphs. If I made a mashup for like bipartiteness in general, it would be like very, very long. Okay, so let's do the code now. I would suppose there's nothing better to do. So we'll read in the vertices and the edges as always. Then for each edge, we'll read in the edge. I can't type apparently. Then once again we'll use the same representation. Edges u dot push back v, edges v dot push back u. Right now, bool this. And then the color, we also keep track of those. So for each vertex, we do the same thing. We're going to mark components. If not visited I, DFS I 0, where 0 is the color. So now we're going to define DFS. And in fact, we're just going to maintain this variable possible. And whenever we find a contradiction in DFS, then like it means that we're going to set possible to 0, and then eventually we're going to check that at the end. So we keep track of the vertex, and then we also keep track of the color. So if visited v, return. Otherwise visited v equals 1. Then we set the color to be this, so color of v is equal to the current color. Then for each edge coming out from v, as always, if not visited x, and we have to have an else clause here, because if some vertex has been visited, then we need to check if this color isn't a contradiction. So if this color is the same as the color of this other vertex and both of them have been visited, then we do have a contradiction. So it's not possible. We have 2 vertices that are forced to be the same color, so it's not possible to do it. Otherwise, we visit that vertex and we go to the opposite color. XORing it with 1 is simply a bitwise magic trick to make it so it just means the other color. I do these things to make it educational. Right, so if it's possible, what do they want us to do? They want us to print yes. No, we just print, okay. Let's see. So we're gonna just like count the number of each vertex. So We're just going to count the number of zeros, or the number of things that are colored 0. Then we're going to print all the ones that are 0. Does it say non-empty? Oh, it wouldn't be empty. Okay, fine. That works then. Yeah, then let me do the same thing here, except now it's just 1. And otherwise, we just print -1. So yeah, that would do it. 3, 1, 3, 4. Is that right? Yeah. So this sample is very simple. It's just this, and then I chose these 3 to be blue and then the other one to be green. And then this one should be impossible because it's an odd cycle. It's in fact the simplest odd cycle we have. This is just that's just this. Yeah, okay. So we're checking bipartiteness, we're doing stuff, it should be great. This mashup is going to take a while. Could you do a bitwise negation? Yes, we could also do like not C or not C, I guess. Or actually not that, but well, either way. I think you would want to do a logical negation, but either way, yeah, I think negation should work too. Shouldn't be that bad of a thing. Let's see what's happening. Yeah, I did get a tablet for Christmas, so that's cool. It's a Wacom Intuos. I don't know its model beyond that, but that's what it is. Has my school reopened? Is that me or someone else? Well, my school personally has not, and will not for a while. And in fact, I think it's going to be optional the rest of the year, so that's cool. They had like a really weird plan for schools. Basically what we're going to do is like, it's going to be virtual but in person. It's like basically people are going to be in the school, but they're going to be at their computers with the teacher in front of them doing the virtual learning. Or like doing the virtual teaching. So like basically on Zoom, but only just in the school. It's like basically the whole thing is pointless. But people want to return, so I guess that's what it's going to be. And then they still support virtual learning, so other people, like I'm still going to be able to connect from home and stuff like that. So I don't really know what the point of it is, but yeah, like you're just at computers in school. The only difference is the location. So anyway, this is E. I will answer that question. I'm also doing web dev, not formally. I mean, I do a little bit, but like not that much. Okay. Why would an odd cycle be bad? Like for a triangle, you could do a vertex cover with 2 and 1 nodes. Well, no, because with a triangle, you get this. So these colors have to be different. And because we need 2 separate vertex covers that both are vertex covers, like the whole point is that every edge means that we have to have 2 different colors. If the colors are forced to be the same, then there's nothing we can do because there's no way the green vertex cover can touch this edge. That's the underlying idea behind it. That's a lot of drawings. I'm going to be doing a lot of drawing today. That's how graphs work. Usually it does help to have paper in front of you or things like that. Which language do I use? I know Python. I know some amount of Java. In fact, I've done some competitive programming in Java, like Kotlin Heroes. I know some Node.js. That's been a fun time. And I don't remember the other ones. I don't think there's that much. So let's see. Now we have the problem E. So the bare Limac examines a social network. Its main function now is that two members can become friends. However, we want a reasonable network, and that means that if two nodes are friends with each other, or like if we have two nodes that are connected, then they should also be friends. That's the graph-like definition. So we have, the way they say it is A, B, and C. So friendship should be transitive. That's basically what it means. That if A is friends with B and B is friends with C, then it also means that A should be friends with C. So this edge should exist for the graph to be reasonable. So if this edge doesn't exist, then the graph isn't reasonable. So another way to think about it is that for every node that this is connected with, it should directly be friends with it. So what is this graph going to look like? What are we want to find out if the network is reasonable? So like, what does that even mean? Well, what does it mean? What it means is that like consider some graph. Let's take 4 vertices. Or consider some component. Let's take 4 vertices in it. Now we know that because friendship has to be transitive, we know that this has to be connected with this. We know that this has to be connected with this. And we know that this has to be connected with this. That would be 6 edges, yeah. In other words, for each component, every vertex has to be connected to every other vertex, right? So somehow we have to check that. And well, one thing we can do is we can check it directly, or we can sort of also like use some smartness about the edges. So we can, for example, one way to solve this would be find the component of every vertex, like find the component ID or something. And then for every vertex, look at it, and then go through all its edges and count the number of edges that go to edges in this that go to other vertices in this component. And then if this for each vertex is equal to the size of the component excluding this one, then it means that like we just directly checked the definition, so it would work. But otherwise it'd be impossible. And a way of defining this component is that it has to be complete. A complete graph, I think. Wait, is that right? Complete? I think that's right. I'm a bit tired, but yeah, that a complete graph would be like every node in a component is adjacent to every other node. That's just like the definition of what this is. So we can literally just check the definition. Or we can do some stuff with the edges too. So say a component has 4 vertices. So every vertex, each of the 4 vertices, must be connected to 3 other ones. Oh wait, no, that's like bad drawing. It has to be connected to 3. Right? So in total, we have to have 4 times 3, which is 12 directed edges. And directed just means like this has to be directed towards this. We don't care about whether this is directed towards this. But the idea is that like for each vertex, it has to be able to reach every other vertex. Then to convert it to an undirected one, well, a single undirected edge contributes 2 directed edges. So it really means that we have to have 6 undirected edges. This is a weird color scheme I'm picking, but just go with the flow, I guess. So we have to have 6 undirected edges, right? So if we have x vertices, then we have to have x minus 1 edges for each vertex. And then we can divide by 2 because each undirected edge gives us 2 directed edges. So the number of edges we need to have in a component is x times x minus 1 over 2. Which happens to be equal to x choose 2. So a separate way to think about this is just saying that like for every pair of vertices, they have to be connected to each other. So we have to have an edge between them. Do we have multiple edges? Is that a thing? No, okay. So no edges repeated, meaning that like we can't have it would be annoying if we could have this, for example, where you have like two separate edges that connect the same nodes, but that's not possible. So really all we have to check is that for each component, the number of edges in that component is equal to this size. Okay, so we can do this. This is doable. But it's a graph stream, so I want to be diverse in what I'm doing. So I'm going to use this opportunity to explain how DSU works. If you don't know DSU, that's fine. I will explain what it is. If you do, great. That should be familiar to you. So DSU is a data structure. It stands for disjoint set union. Other people like to use a different acronym, which is UFDS for union find data structure. Either one works. It doesn't really matter what you call it. The point is it does the same thing. Wait. But it just means that if you've heard that terminology before, you could be thinking about the same thing. Basically, the idea is it does two things. You have a bunch of nodes. It'll do two things for you. One, it'll allow you to add an edge to the graph. And two, it will let you ask, or it will let you ask certain things. Like you can find the component that a vertex is in, or you can ask, are two vertices in the same component? Or you can also find the sizes of each component. You can store a lot of information about each component. So a better way to think about it is something like this. So it does two operations. One, you can add an edge. What adding an edge will do is it will sort of like merge two components. So if I add this edge here, it will merge this component and this one together. And if I add this edge here, meanwhile, the DSU will know that these are already in the same component, so this edge will be sort of ignored. Yeah, so you can add an edge and merge two components, or you can ask information about some component or some vertex. Yes, you can do it using only BFS or DFS. I'm just going a bit advanced because I want to talk about this at some point. But it's similar difficulty to the previous problems. You don't need DSU for this. So if I want to ask about a vertex, for example, I can ask the component that some vertex is in, and then I can also check if two vertices are connected by asking, hey, is this component equal to this one? And if so, then yes, otherwise it's not. But I can also ask about a component. Like I can ask for this component's size, for example. Getting some cough stuff here. Yep. I can ask about the size of a component, for example. Or I could also store the number of edges that run through some component. And that way I can use DSU to figure this out. So this is its basic functionality. And I'm going to explain very briefly how it works. Let's take a lot of vertices. There are plenty of DSU tutorials on the internet, so I don't think it's worth it to cover it for a long time, but also I'm going to go over my own implementation, which is not the fancy complexity of O of n times inverse Ackermann n. This is a very weird complexity, and it's a very weird proof, but it's generally the common complexity of DSU. But I'm going to go with one that's sort of more intuitive to me, but it's slightly worse. It's O of n log n, which is still very fast, but this is the only thing I'm able to explain, so we have to go with this. If you want a faster DSU, you can look more into that, like some other websites or something. But this is going to be union by size. So let's say we receive some query to merge two vertices. Or for example, we start with every vertex sort of having its own component number. So we're going to merge two vertices now. So now these two vertices have to be in the same component because now they have an edge between them. So what we're going to do is we're going to relabel some of the nodes to be in the same component. So for example, I'm going to pick 2, and I'm going to label everything that isn't 2 to be 2. Now say I merge these two now. Now all of these have to be the same component. So for example, I could pick 8, say 8 is going to be the dominant one, and then everything else in this component that isn't 8 will be relabeled to be 8. Right, and then I'll do the same thing. And maybe I'll merge these two, and now these will be relabeled to be 5. And then I can merge these two, and then these could be relabeled to be 8. And etc. So that at every stage, we know the exact component that every vertex is in. But we could have a problem. Because look at what we were doing before. Say, for example, I do this merging, and I say this is going to be joined in with this component. Now, if I say 6 is going to be dominant, and I relabel all of these vertices to have 6, every single time, then every connection is going to take at worst O of n. Because the component size is going to be of order n, and we're going to do order n merges. So really, the time complexity is going to be n squared, which is pointless. It doesn't really help to do that. But we can do better. And the way this log, the reason this log comes into play is because we're going to be smart about what we relabel. Specifically, when we merge two components, say we add this edge. In fact, I'm going to do this here. When we merge two components, so we're adding in this edge, we're always going to relabel the smaller component. So because there are more 8s than there are 6s, we're going to relabel the 6s instead of the 8s. And then these are all going to become 8s. And notice that we can do this with a simple DFS because we have some component here, and we have some component here, and they're like disjoint before we add this edge. So we can DFS in this component and set everything in this component to be 8, and then we add this edge. Okay, but the way this would work is now, like, what gives, right? I mean, this could still be bad. Say we have like one component of size, one huge component of size n over 2, and another huge component of size n over 2, and then we merge them, right? Well, it's going to take the minimum of the two, which is still going to be n over 2. So, like, what gives? That's bad. That's still n squared, right? I claim that it's not. And even though a single operation can take O of n time at worst, all of the operations, well, first also we do at most n-1 merges, because if two nodes are in the same component, we ignore them. Every merge decreases the number of components by at least 1. So we do n-1 merges. And I claim that the total over all the merges is going to be n log n. So it's going to be O of log n average. Or another way to think about it is amortized, which is sort of the same thing. Underline them both. Yeah. So, and the reason this is so is because, let me prove it. Consider some vertex. Like, just take some arbitrary vertex. Initially, it's in a component of size 1. And we're gonna count how much this vertex contributes to the complexity. And then the total complexity will be the sum of the contributions for every other vertex. This is like contribution to the sum. So when we merge this vertex into some other component, say this is the bigger one, then we don't care about it. This is the bigger one, so we don't care about it, so we're going to make this one, right? But say we have some larger components. Say we have a component of size 3. Then we're going to merge these two, and now we have to relabel this component. We have to relabel this node because it's in the smaller component. But note that this goes from a component of size 2 to a component of size 5. And if this component is the smaller one, like say this is a component of size x and this is a component of size y, and we're merging x into y, then the new component we have is of size x plus y. And because we know that x is less than or equal to y, then x plus y is greater than or equal to 2x. Which means that we're moving from a component of size x to something that's at least 2x. Meaning that every time we merge this vertex, the size of its component will at least double. Or every time we relabel this vertex, the size of its component at least doubles. How many times can we double? Well, we're interested in how many times we can double until we get to n, which is the definition of the logarithm. So that's it. Every vertex is relabeled at most log n times, so the total complexity is n log n. Mic drop. Yeah, that's basically the way that works. So to do DSU, we literally just like naively merge the components where we merge the smaller one into the larger one. And then we can ask, and then when we merge two components, we can also merge the information. So when we're storing the size of a component, when we merge this into this one, like this just gains the size, and the number of edges in the new component is just the sum of the previous ones. So oftentimes the implementation is easy to keep track of. Anyway, doing DSU sort of solves a harder problem. Like we could do something like, given each edge, when we add an edge, we want to, like, we can say that like we're going to add a bunch of edges. Each time we add an edge, we want to figure out if the graph is still reasonable or not. So like for each edge, when we add them in some order, after we add the first I edges for each I, is the graph reasonable? And that DSU would let us do that, I think. Sort of, yeah. But anyway, why are we not using BFS? Just because I just wanted to make it a bit more complicated. Because I wanted some way, I wanted some context to explain DSU, and that's basically why. So we're going to read in the graph, and we're going to code DSU as well. We're going to code this n log n form of DSU. So we have edges. We're basically going to say merge UV. So here's what we're going to do. We're going to keep track of edges. Size 150,000. We're going to keep track of the label of each vertex, and we're going to keep track of the size of each component. And now do some comments. In this implementation, we can do find an O of 1. That is correct. So let's do some merge now. And also we need the count of edges because that's sort of important. So according to my smart fans, all these will be initialized with 0, so we don't need to memset them. Yeah, I just want to show DSU because I want to show some variety. So we're going to read in the edges. When we merge two vertices, so this is the component of U, so this is the label U, and CB is the label of V. So we're gonna assume that like the size of CU is less than or equal to the size of CV. And if not, then we just swap them so it's true. And then the way that works now is that now we know we're going to relabel CU because CV is the larger one. So now we can do stuff like relabel. How'd this work? Okay, relabel. So I'm going to define a function called relabel now. So basically, we're going to just like set the set all the vertices in this component to this target value. So this will be relabel U to be the component of V. Oh, actually, I also need to swap U and V in this case. So how will this work? So if label V is already equal to the target, then we've already relabeled this vertex, or it's part of the, or it's already part of the larger component. Either way, we don't need to continue it. Otherwise, we set the label V equal to the target. Then for each vertex adjacent to this, we relabel all of those. And also, we need to add the edges in. Just like standard adding an edge. And yeah, that'd be how that works. So now we need to do some more stuff. So we need to do size CV plus equals size CU, because now we're merging CU into CV. And n edges CV plus equals n edges CU. And yeah, that's it. So yes, it is necessary to return if they're the same. So if CU is equal CV, we don't want to merge because then we'll have inaccurate sizes, so we return. But before we do that, we also need to add another edge into this component because we know we did that. So we would add an edge to one of them but not the other because we don't want to overcount, so I'll just pick CU arbitrarily because either way they'll be merged by the end of it. So now we're maintaining the number of edges, we're maintaining the size, and we're doing relabels. So yes, find in this case will be O of 1 because we already know the components for everything. Right, so now we for I equals 0, I is less than 9 plus plus. For each vertex, well, we can do for each component check the condition, but it's the same as checking for each vertex for the component it's in, does the condition hold? So really it's just if, so what is this? Size of the component of I. It should be that the edges, the number of edges should be equal to the size, should be equal to x times x minus 1 over 2. So the number of edges and edges label I is equal to times size label I minus 1 over 2. Or if it's not equal to, then it's not possible. Then we just do some magic ternary. If possible, print yes. That's what we want, right? Otherwise, print no. And yeah, this problem should be by Ricto, I think. He does like to use that theme. Let's see, did I intentionally forget anything? I don't think so, right? Alright, that's a problem. So we get no for the first answer, which is not good. Isn't edges a one-dimensional vector? No, it's a list of vectors. So, yeah. Alright, what am I messing up? So when we merge, we need edges U to be V and edges V to be U. Oh wait, I need sizes to be 1 initially, otherwise it makes no sense. Yeah. Every component is size 1. And actually, also we need them to be in different components. Actually, yeah, we do. Jesus, I can't speak. We do need to do some initialization. That we can have the number of edges be 0, but the label of I has to be some unique value. So we can set the label of everything to itself, so that everything is initially in its own component. And to add to that, every edge is, or every node is a component of size 1, because that's just what it is. It's initially by itself. Yep. Sounds about right. Let's see, we go up to 150,000 for no particular reason. And, yeah. Cool. Cool. So yeah, again, it is indeed possible to just do this with normal DFS or BFS or whatever you really want. But I preferred to do it with DSU to just have it as an example. But it's not necessary. So anyway, that would be that. Can get rid of all of this now. In the timestamps, I'm going to explain what I go over at each step because I'm going to be solving problems unconventionally. So if you forget where DSU is, it's on problem E. I'll have it in the timestamps. Also, we'll go over DSU again later because it'll be necessary. Alright, this is where it gets harder, according to people. So, hope you are looking forward to that. I'll set the current problem. Or not. If I can click it. Alright, this is a struggle. That was, yeah, that was a struggle, sure. If you're looking for some intentional struggles, that wasn't even on purpose, but there you go. That should be pinned now. Okay. Alright. You have a graph with n nodes and m directed edges. Directed is important. One lowercase letter is assigned to each node. We define a path's value as the number of the most frequently occurring letter. For example, if letters on a path are abaka, then the value of that path is 3. Your task is to find a path whose value is the largest. Okay. So, that's it. We have a graph. We have a directed graph. Each thing has a letter on it. So for example, let's construct this from the sample. It is abaka. Indeed. So what they do is they have directed edges. So we have one from 1 to 2. We have one from 1 to 3. We have one from 3 to 4. 3 to 4. And one from 3 to 5. So what we're going to do is we're going to take a path. We're going to create the string taken by like having the letters on that path in some order. And then the score for that string is the maximum, well, I like this color. It's the most frequently occurring letters. I don't think I've used any of these other colors much. Cool. Anyway, getting sidetracked as usual. But yeah, the value of a string is the frequency of the most frequently occurring characters. Okay. And if the value can be arbitrarily large, which is sort of an interesting thing, what happens? So when can the value be arbitrarily large? Well, it doesn't say that we have any constraints on visiting, meaning that we can like visit any vertex multiple times. So say we have a cycle, right? What happens if we have a cycle? Like say we have A, B, C. Well, if we go on this cycle, like I can start here, and I can go here, and I can go here, and I can go back, and lose my streak like instantly. And I can go back, but then I can go back again, and I can go back again, and I can go back again, and then keep going and keep going, and you know, just like keep going in the cycle infinitely, right? So that's a problem because I can get a string of infinite length like this. I can get ABC, 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 and then my score would literally be infinity. So if we have any sort of cycle in this graph, then the answer is -1. There's no possible, like there's no answer because the answer is infinity. For every finite answer, I can make it larger by going around the cycle again. So immediately, if there's a cycle, there's no answer. So let's write that out. Cycle, no answer. Otherwise, there's not a cycle. So when there's not a cycle, we get this special kind of graph. And this graph is called a directed acyclic graph. Or more commonly abbreviated as a DAG. So it's directed because it's directed edges. It's acyclic in that it has no cycles, and it's a graph because it's a graph. I don't know what to say there, right? So in this case, this is a DAG because it has no cycles and it's directed. Something like this would also be a DAG. Let me draw something a bit more complicated. For example, like this. Boom, boom, boom. So I can draw something like that, and then 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 like that. Right, now this doesn't actually have any cycles because I think that if I drew it right, it shouldn't have any cycles. Yeah, because like here you can go here, but then you can't ever get back here, and here you can go here, but then you can't ever get back here, or you can go here, but then you also can't get back here. If you go this way instead, you still can't get back here, and then like it doesn't have any cycles. But anyway, so DAGs can be still complicated. Even if they don't have cycles, they can be very, very complicated. In fact, I can even add more edges. I can add this edge, and this edge, and this edge, etc., and this edge, and this edge, you know? As many edges as I want. Make the drawing very messy. But one cool thing about a DAG is that there's this thing called a topological order. And what it means is that I'm gonna assign a number to each vertex. It's gonna be distinct. So for example, we have 6 vertices, so I'll give them all a number from 1 to 6, like 6, 5, 4, 1, 3, 2, right? And so a topological order, I'm gonna write that out. Topological order. The way it's going to work is topological order, also known as a topological sort, which is probably a more common way you'll hear it. So topological sort is a way to order these vertices so that every edge goes from a vertex of a lower number to a higher number. So for example, this would be violated immediately because we have an edge from 6 to 2. But this edge 2 to 3 doesn't violate it, this edge 2 to 4 doesn't violate, and 1 to 5, for example, is also fine. So imagine we had this order. Let me, for example, write some example order out. I'm repeating example again. I remember in one of my old videos I said like example for example, and that was like memed out. And that was rightfully so. So if I do something like this, 1, 2, 3. Actually, yeah, there is only one topological order here. It's this. That now we can see that every edge goes from a vertex of lower number to a vertex of higher number. And so the reason it's sort of like a sort is because they're like sorted by their like it's like a weird metric of like accessibility. Or like it's sort of like their level in the graph. Like every like the vertex at the highest level has nothing going into it. So it just means that like it's at the beginning of the sort because it's like the highest up. And then later down we have something that's lower but still pretty high, and then as we go down the sort we get lower and lower. So this is something we can work with. So what we want to do is solve the original problem. We want to figure out the most frequently occurring character. One thing we can do is, this is not an easy idea perhaps to figure out, but the idea is we can fix the character that's the most frequent. For example, say we're interested in A's. Say we want A to be the most frequent character. If it turns out that the most frequent character is some other character like B, then assuming that it's A will only make our answer worse because B is a better answer. So if we try this for all characters, when we consider B later on, then we'll find a better answer. So even if this is wrong and the most frequent character is an A, it doesn't matter because we're getting a worse answer by making that assumption. So really we can just assume that the most frequent character is every possible character and not care about being wrong. And in general, when you make such an assumption and the violation of the assumption means you'll get a worse answer, it means that if the assumption makes the implementation more convenient or it makes the problem easier to solve, go for it. So that's what I'm doing here. We're assuming that the most frequent character is A. And then we'll do it for B, and then we'll do it for C. And then for every character. So now, really, if we convert all these values to 1 if they're A and 0 if they're not, then we're interested in the path with the highest possible value. So now we do this with dynamic programming, I think. This should be a thing. I don't know if there's a better way to do it. I don't really see one. So, let me see. So, yeah, the way to do this is with dynamic programming. If you don't know what dynamic programming is, check out my earlier streams. That's the best advice I have for you. I don't want to explain. It's sort of complicated, so I don't want to explain it all here. But the basic idea is we let dpi equal to, we're solving for this value dp, where dpi is the highest valued path ending at I. So now the recurrence for dpi is dpi is equal to the max over all j where j has an edge to I of dpj plus 1 if, like, for example, the character of I is our target. So for example, if we have an A at I, then we get an extra one. And if this doesn't exist, if there's no possible J, then it can also just be 0. So we start at 0 and then we take this maximum. So, yeah. So the reason this is convenient is because if we find this topological order, or this topological sort, then the order in which we want to go through the dp values is through this sort. Because that way, or it may be in reverse depending on how you do it, but actually no, it is this way. That, like, for example, we go here, and then this has no vertices going into it, so that's not how it the answer here would just be whatever it is. But then we go here, and we know that how am I not able to erase that? Okay, so we go here, and then now we've already visited this vertex, so we know that the dp value of this is correct because we just computed it. And now we know that every other vertex that this dp relies, this like dp transition relies on, is already computed because of the topological order that every edge goes from a lower value to a higher value. So because the way the topological order works, that this this transition will only rely on lower values, because j having an edge to I means that it should be earlier in the topological order. This works, that well, the DP will be correct because we're computing it in the right order, or we're computing it in a right order. And actually, if you want to think about this a different way, topological sort is very involved in DP, or rather, like the way DP transitions have to be required to work is that the relations between them have to form a DAG. Like if okay, actually this is going more complicated than what I'm able to explain intuitively, but the relations have to form a DAG. Like if we're going to compute this, we have to have computed everything else sort of like before. Voice crack, nice. we have to have computed everything else before, meaning that the order in which we compute the DP values has to be a topological sort on the directed acyclic graph of transitions. So it's sort of like slightly mind-blowing, slightly intuitive, but don't worry about it if it's not easy to understand. Don't worry about it. It's not that important. The point is we're going through the topological sort, and then in that order we do DP. And we find the topological sort once, and then we do DP independently for every character, and then the answer is the maximum. Okay, wait. So there's some discussion about not using topological sort. So using vectors. I mean, doing DFS from an arbitrary node and then doing that while they aren't visited is literally the algorithm for topological sort. Like, I mean, you can say it's not topo sort, but you're basically doing it like you're embedding the DP inside the topo sort and just not explicitly computing it. Like, it's the same thing. It's just implementation wise. Like, it is topological sort. It's the same code. You're just not generating the order. It's not using a queue. Okay, I mean, however you do it. Wouldn't you still need a queue for it? Anyway, I'll go over how to compute a topological sort too. So, for example, I'm holding my pen backwards again. Let's take this graph. I'm going to do things in a very specific order. So we'll draw like this, like that, like that. Oh, memoization? Oh, I guess that works too. Yeah, that's true. Okay, that's fine. But I want to teach topological sort anyway. Okay, wait. Again, I'm drawing these edges in a very specific order. I want to be able to undo this later. So, let's see. So we do this. Let me draw this edge, and then this edge, and then that. And then we draw this edge, and then this edge, and then that. And then we draw this edge, and then this edge, and then this edge, and then that. This is the ugliest node you've ever seen. But, right, so that's the idea. The basic idea of topological sort is that we're going to start with a vertex that has 0 in degree. And the in degree is simply the number of vertices that go into it. So, for example, this is the only vertex that has 0 in degree. And what it means to have 0 in degree is that there's no edge that goes into it. So if we're assuming we're going to like place the values 1 to n in the topological sort, because there's no vertex that has an edge to it, there's nothing that this value has to be greater than. Because like having an edge means that this value in the topological sort has to be greater than this one. But because this has in degree 0, there's nothing that this value has to be greater than. Meaning that it's okay to make this the next position in the topological sort. So then once we do, like we can, for example, assign this the number, we can assign this the number 1 in the sort. Then once we do, the trick is we remove this node entirely, because now it's not relevant anymore. We know that because this is the earliest currently existing node in the topological sort, then this edge being less than this one is going to be satisfied, this is going to be satisfied, and this is going to be satisfied, because these are all going to have higher labels than this one. Meaning that now we can ignore the rest of these edges because we're constructing the order from 1 to n. So these edges are satisfied, so we can get rid of them. We can ignore them now. So it means we get rid of this vertex and all the edges. And now you see why I drew it in this specific order. So now we have this new graph, and we do the same thing. We look for a vertex with 0 in degree. As it turns out, this is the only one. So we continue. Now this gets assignment 2, as we've already shown, and then we remove this vertex. Now this is the only vertex with 0 in degree, so once again this gets assigned 3, and we remove this one. Now this is clear. We just simply this gets 4, this gets 5, and this gets 6. So that's how that works. We look for any vertex with 0 in degree. If so, we remove it. Say it's the current position in the topological order, then move up one position and then remove that vertex. And then the topological order is simply the order in which we visit vertices. Now, how do we check for cycles? That's the other part of the problem. That's the last part of the problem, in fact. Because now we know how to do toposort, we just need to check for cycles. This is a lot of things in one problem. I don't know how this is a 1600, but say we have a cycle, right? So that means that this goes into this. This goes into this, so this has a degree of 1. This goes into this, so this has a degree of 1. And this goes into this, so this has a degree of 1. Right? In a cycle, it's going to contribute an degree of 1 to every node in the cycle. Meaning that at a certain point, we're never going to be able to remove this cycle because no vertex in this cycle will have degree 1. So if we have a cycle, this process of removing nodes with degree 0 will fail because we'll never have, these vertices will never have degree 0. So if we have a cycle, that means that our process will fail. Conversely, if we say that our process fails, this is how you prove things. You can show that they're logically equivalent to each other. If the process fails, then what happens? Well, it means that at some point, there were no vertices within degree 0. Right? So it means that if we have no vertices within degree 0, within degree 0, let's show that this implies that there's a cycle, right? So we have this. We have some vertex. Now it has something going into it. Right? So now let's just trace the path back up to this vertex, to any vertex that goes into it. So now once again, we have this, and now this doesn't have degree 0, so it means it has some vertex that goes into it. Let's go up this vertex once again. Now this doesn't have degree 0, so it has something that goes into it. This doesn't have degree 0, so it has something that goes into it. And eventually, we're going to visit some node that we already visited, because no node has degree 0. So from every node, there's some parent node that we can take and go back up the chain. Until eventually, by pigeonhole principle, after n+1 steps, we have to have visited some node twice. And so it means that, now tracing this path forward, this is like a cycle going backwards. Because we started at some vertex, we traversed some edges, and then we ended up back at that vertex. That's what a cycle is. So if there's a cycle, then the process will fail. And if the process fails, then there's a cycle. So it basically means that this process failing is logically equivalent to there being a cycle. So it means that they're the same thing. So really, all we need to prove was this part, but I just did both to flex. But basically, we try this process. If it fails, we have a cycle. And if it doesn't fail, the point of proving them logically equivalent was that if it doesn't fail, we don't have a cycle because we just found a topological order. We have it. We just found the order. So if it doesn't fail, we're just done. So we run this process. If it doesn't visit every vertex, we have a cycle. Otherwise, we do. So we have a topological order. So we do DP. That's how it works. Pen drop instead of a mic drop because my mic is, I don't want to drop it. Yeah. So let's write the code then. So we read in the number of vertices and the number of edges, then the string. Now vector LL edges 300,005, and then we also store the integer. And of course these are initialized to 0 as I've learned. So for each edge, an edge from x to y, 0 index, then edges x dot push back y, and y gets a new vertex that goes into it, so its integer is incremented. Cool. So, now the way we do this process is we simply sort of do it like BFS, where we insert nodes into a queue, and apparently other people do it differently. You can do memoization with DP or something, but we insert nodes into a queue, and that's it. That, like when we remove a vertex, or when some vertex is in degree 0, we insert into a queue, and then like BFS, once we remove it, we remove all of its connections, and then we sort of check those and continue in standard BFS order. So let me show you what I mean. So we have a queue of the current vertices with in degree 0. And also we'll count the number of vertices we visited. So for each value, if its in degree is 0, q.push I. Now, while we still have stuff in the queue, it means we still have stuff to process. We also need, actually no, we don't need visited, because we'll only visit a vertex once when it's in degree 0. So plus plus count, because we have a new vertex. X equals q dot front. Right, then q dot pop, get rid of the front. Then what we're gonna do is for each node outgoing from X. Oh wait, also we're gonna keep track of the topological sort itself because we want to do that for DP. So for each node adjacent to X. Now we're removing X, so we want to remove this edge from X to Y. If in degree, then we remove that. Y is equal to 0. Q dot push Y. Because now we're looking at that one. So if count is less than n, then immediately we print -1. Otherwise, we go on. So for first, keep track of the answer. We're going to iterate through the character. And we're going to say memset on the DP. Actually, I don't technically need to do that, but whatever. So now we're going to iterate through in the order of the top of sort. Yeah, and then this is the way I'm going to do this is sort of weird. Instead of like doing this transition directly, I'm going to like, it's sort of like the same idea of push DP that I've sort of thought about for a while, that we sort of like consider how this value of DP affects the future ones. So like, for example, for each I, then for each j that it can reach, we would do something like dpj equals dp of I, for example. Instead of fixing some I and doing all these transitions at once, we're going to sort of reverse it and figure out how this one will affect all of its future ones. But it's the same idea. So for each edge outgoing from X, so first of all, actually, if this character is the same, C, then we get a new value at this, so we have to increment the dp value. Then there's just sort of implementation. dpy equals max, dpy, dpx, because now we can come from X to go to Y. So that does it. So that's topo sort, then we do some dp. And that's basically it. Should get 3. Should get -1, and then we print some. Should not print that and the answer at the same time. That's dumb. -1. Here we get 3. Here we should get 4. Very complicated graph, it seems. Yeah. Alright, so let's make sure everything's good. 300,000. Yep. And do some stuff. Q dot front, top of sort, dot pushback X. Then we just go for it, man. Yep. If you get it wrong, it doesn't matter. It's a mashup. It's no penalty. But it's accepted in 1076 milliseconds. That's a bit concerning, but I don't know where that came from because this is only 300,000. But maybe like the vector iteration is that bad, so maybe it's not the best idea to do that, but whatever, we're gonna be fine. It does pass anyway. Maybe I should have put I earlier, but you know, whatever. In fact, I think I is like strictly easier than H, so maybe we'll do that. Although I don't want to reorder at this point. So this problem is done. Just gonna remove all of these. The farther we go in, the more notes I make. Okay, so we have this. Well, I'm going to go to the bathroom first. It's been like 3 hours. Yeah. So let's see. What should I draw? What should I draw for the intermission thing? I can do like the standard that, and then can have like a cycle around it. Yeah, sure, that works. All right, have fun. I'll be back in a couple minutes. Probably get more water too. Alright, hopefully that did not cause audio problems. So, yeah, that'd be ideal if that didn't happen. I guess that works. So we return. So now we're at G, and continue this thing. So this problem is mine, but like also like not really. Like I sort of just stole it from I and then made it so it's like shortest paths instead of like a spanning tree. But yeah, so basically the idea is you have a graph, a weighted graph with by the way, the audio is good, right? I hope it didn't break anything when I turned the mic off. So you have a weighted graph, for example, like this, with 3 vertices. And then you have edges between them, like so. So then you have an edge with cost 7, and a edge with cost 4, and an edge with cost 2. So a weighted graph is simply that every edge has a number associated with it. And let's see. Yeah, so every edge has a like, okay, I just wanted to make sure the audio was working. So every edge has a cost associated with it. And then the cost of a path is simply the cost of the edges that you go through to get there. So this would be 2 plus 4, which is 6. And if we take more edges, it would be more. So the shortest path between 2 vertices is simply the path with the smallest amount of cost. So it would be this one, because even though this has only 1 edge, its cost is 7, which is higher than this path's cost of 6. So shortest path is simply the path with the smallest total cost, or smallest total cost. So we have a weighted graph, and we're asked to find the shortest paths on each of these graphs, except we have something else as well. We have array values that correspond to each thing. And for each pair of vertices, we can travel between them for a cost of the sum of their array values instead. Now in this particular sample, it's never actually optimal to use any of these, but in other cases it may be. So for example, say I made all these values, like say I made this 1, 1, and 3. Then I can travel between these two for a cost of 4 instead. I can travel between these two for a cost of 2, and these two for a cost of 4. So it's like we have more edges to work with. Okay, so there are 2 things we have to go over. First, the solution, and then also how do we do shortest paths. There's a well-known algorithm called dijkstra's, and the spelling is quite interesting. So let me relabel these. There's an algorithm called dijkstra's, which is dijkstra, which basically does just this. Given a starting node, it will find the shortest path from that starting node to every other node at once. So it'll find the shortest path to vertex 2 and vertex 3 and vertex 4 and vertex 5 and vertex 6 and vertex 7 and vertex 10 to the 9th, all at once in a total of O of n times log of n. So yeah. So assuming we have that, well, actually, dijkstra's is sort of a prerequisite. So before I even start with the rest of the, let's just get started with this. So how does dijkstra's algorithm work? I'll just respell it again. How does dijkstra's algorithm work? So you have a graph, and you're going to start with something. It's actually like really simple to explain, but it's harder to prove. We have something like this, for example, and like this, 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 maybe. And we're going to say like this is 2, this is 3, this is 5, this is 7, this is 10, this is 2, and this is 4. dijkstra's also works on directed graphs, but I'll assume it's undirected for simplicity. So the basic idea is we pick the starting node. Then the algorithm is literally to just look at all other nodes and take the one that's the shortest distance away. So like, for example, from this node, we can reach these two. And the sort of shortest distance for this node is 2, and the shortest distance for this one is 3, right? So it's as greedy as it gets, basically. We're just gonna look at this node and take the next node that's the shortest distance from it. So this is distance 0, this is distance 2, and this is distance 3. So now this node is locked, like we've already visited it. And so now when we visit a node, we're gonna visit 2 because it's the shortest potential next node we have. Then this is also locked. So now we look at how this node affects the other ones. So for example, we can go from here to here with the cost of 2, because that's what it took to get here, plus 5, the cost of the edge. So this would give us 7, but that's not good. We already have 3, so it's pointless to include this. But we can go from here to a cost with 2 plus 7, which is 9. So this is sort of the potential. And so now the smallest node we haven't visited yet is 3, so we lock 3. Then that doesn't affect anything anymore because all these edges are already obsolete, so now we lock 9. And so when we visit 9, we can go here with potential 19, or we can go here with a potential 11. 11 is better, so we lock 11. And now we can go from here to here with a cost of 15, which is better than 19, so now we make this potential distance 15 instead. I'm using potential wrong. There's a separate thing called dijkstra with potentials, but don't worry about it. I'm just saying, like, this is the current distance we have, the best distance that we could possibly reach this node at. So that's it. That's the algorithm. Like, you straight up just pick the distance, you pick the node at the shortest possible distance that's not been locked yet or not been visited yet. It's sort of iffy how it works when you have negative values, because like if you have a negative cycle, like for example -1, 2, and then -10, like it's optimal to just like keep going and keep going and keep going and get negatively infinite cost. So that would not work with dijkstras. In fact, I'm not sure if it works with negatives at all. It may just not work. It either doesn't work when you have a negative cycle, or it just doesn't work at all. I'm not entirely sure. That's something that can be looked up, but it doesn't matter for this mashup, so I'll leave it be. But that's the idea. So this is n squared if we consider all the possible nodes every time. But if we use a priority queue or something to represent the set of the unvisited nodes we have, so for example, say I've visited these 4, then in the priority queue, I would have that we can visit this node at a cost of 11, or we can visit this node at a cost of whatever it was before. This would be 19 before. And in the priority queue, you take the minimum element every time, and you visit that one, and then you update the new distances. So that would be how that works. Yeah, but other than that, it's sort of a bit more complicated. What we're going to do is, I don't know what I'm saying. Yeah, that's how dijkstras works. So, why is this relevant? Well, now what we're going to do is we're going to we have to solve this problem now. So there are 2 ways we can solve this problem. One of them is just bashing it out, and the other is sort of more analytical. So I'm going to go over both possible solutions. So let's say we have some graph. Say for example like this. Like this, I guess. And this is like, so we can say it says cost 3, cost 4, cost 7, cost 6. This is for totally random numbers. Cost 2, cost 1. And these array values are something like 3, 5, 8, 9, what number am I missing? 4, 5, 6, 7, 8, 9. Make this 0. Okay. So now assume we've already locked in these 3. Now what we want to do is, using the, by the way the algorithm works, what we want to do is we want to find the next node with the smallest possible cost. So there are 2 possible ways we can do this. One, we get the smallest possible cost from a normal edge. So this would be simply running the normal algorithm, right? We lock each vertex and we use it to update the new distances. So from each, so the shortest distances to each vertex, this would be 0, because this, assume this is the starting node. Then this would be 3. This would be 4, we can go here. And now the distance here, only using the edges that we already have, are this, we can get here with a cost of 5. And then we can get here with a cost of, well, we can get 6 doing this, but assume we haven't visited this node yet. So now we can get here with a cost of 12. So the first possibility is that the smallest possible cost comes from the original edges. Okay, but there's another possibility too, that the smallest possible cost could instead come from using a special edge, where a special edge is the one where we like use the AI plus AJ cost. So we can handle the original transition, but the new possibility is that we use a special edge instead. So we want to find the minimum cost of using a special edge and also the node that it corresponds with. So how do we do that? Well, what we can do is we can use, like, let's just consider brute forcing it for a bit. So we go through all visited nodes. We can go from some visited node to some unvisited node for a cost of what? Well, if we're going for the visited node I, if we're going from I to J, we get the cost of the distance to I. This is like these light blue values, the locked in distance from the start position to I, plus the cost of the edge, plus AI plus AJ. Notice that there's no term that depends on both I and J, meaning that the I parts are sort of independent from the J parts. So really what we want to do is, we want to figure out, of the nodes that we visited already, which one minimizes this? Or what's the minimum value of this? And then of the nodes that we haven't visited, which one minimizes AJ? And then combining the minimums of these two will give us the minimum that we would ever have from using one of these special edges. Notice that if we keep track of J throughout as well, then we know the node we're going to. So this lets us sort of do it like, but just bashing out the algorithm and understanding how greedy works, that either you take an original edge and you would do the normal dijkstra to figure that out with a priority queue, or you do something else and you try and minimize this expression and you consider the other possibility of using the smaller edges. And in the greedy fashion, whichever one gives you a shorter distance, you would take that one and then you continue the algorithm. So the way to maintain this is, well, we only ever add vertices to the set of visited nodes. So really we can just maintain like a minimum as we go along. For this, we would need something else. We could have like a separate priority queue or a set or something that allows deletions, and that would work fine. But we just need to, we would store like pairs of AJ and then the index itself. Or we can store the index and then use a custom comparator, really however you want. But the idea would be that you, the idea would be that you just find the minimum value of AJ, the minimum value of this, and then combine the minimums. So that's one way to do it. You just sort of bash out the algorithm and can like do dijkstra like it would be normal. But there's another way, and I find it cooler. And in fact, I didn't realize this way was possible until I like thought about it for a while. But there's another way, and it's kind of cooler. Imagine we just made the graph. Let me ignore all the normal edges for now. So assume we're only using special edges with the cost of the array values. So let's say we just made this graph, 3, 5, 0, 9, 8. So we're going to add this edge in. We're going to just make the graph. We're going to make all O of n squared edges. We're going to add this edge in with cost 11. We're going to add this edge with cost 12, add this edge with cost 8, and this edge with cost 3. We're going to do this for all of them. And we get like a star or something. Right, now of course this is O of n squared edges. Dijkstra is n log n. So this would be n squared times log of n, which is not possible. It's not something we can do. But once again, sort of like the other idea, the cost is AI plus AJ. This cost is independent of this cost. So can we somehow make it so we don't have n squared edges in total? Let me draw a new version of this graph. Like here. Consider adding all of the edges that only correspond to this node. What's going to happen is we add an edge with cost 3 plus 5. We add an edge with cost 3 plus 0. We add an edge with cost 3 plus 9. We add an edge with cost 3 plus 8. Notice that we're adding the 3 every time, right? So what if we sort of split it up instead? The idea would be to create some new node that's sort of like this. And then we sort of abstract away the cost of 3 by doing, like we put the 3 here. So we're separating the AI and the AJ parts into separate edges. And then for everything else, we'll create this with cost of 5, and this with cost of 0, and this with cost of 9, and this with cost of 8. Because the 3 is constant everywhere. Because the 3 is constant everywhere. Yeah, so the 3 is constant everywhere. Meaning that like we're just doing the same thing over and over if we keep adding these edges. So we add the 3, then we take 3, and then we add in AJ for every other possible node. Now this is one node. So what if we did this for the next node then? So we add an edge with cost 5 to some virtual node that basically represents using the cost of AI, and then we add new edges with cost of AJ. But wait, look, we just did that. This is a virtual node. This is all the other ones. So doing this and then attaching all these to this virtual node, like sort of almost by accident, we can stumble upon the fact that we only need to do it for one node, and it will be the exact same set of edges for all the other nodes. So that's the idea. We go to this virtual node with cost AI, and then we go to some other node with cost AJ. And that's sort of it. So then this is O of n edges because we make one edge from every node to the virtual node, and we only have one virtual node, so that's it. It adds only O of n additional edges. Or it adds exactly n additional edges. And so the idea here is that every path that we could have taken in the original graph with the special nodes can be simulated here. We can go from any I to any j using this. We can go from I to j using the cost of 3 plus 9, which is 12. And this works for all of the nodes. So that's it, really. We treat the graph normally, but we also add in these special edges like so. I believe there was another way to do it, but I don't exactly remember. Maybe there wasn't. I don't know. If other people have their own solutions, that'd be kind of cool too. But anyway, that's the idea. So this is a lot simpler to implement than using the other one, so I'm going to do this. If you want to challenge yourself by modifying the Dijkstra algorithm a bit, then you can also try the other one, the other approach that's sort of more, that sort of exploits the structure of Dijkstra's algorithm a bit. Anyway, that's how the code would work. Am I missing stuff in the chat? Seems like there hasn't been much. Wait, what happened? Okay, I don't know what happened, but somehow like my chat just completely froze on my phone. I'm sorry, but I missed a lot of stuff apparently. Let me I don't know what happened there. Somehow I missed like everything. Okay. Well, that's annoying. So let me answer questions now. I don't know what I missed, but yeah, true. I should update the problem. Pinned comment, yeah. Audio's fine, okay. Negative weights don't work at all, yeah, okay. Makes sense. This is G. Yeah. Yes, I see the chat now, okay. It was just bugged. Somehow my phone was frozen. And now I got a loud notification from Twitch. Yes, I can figure out. Oh, do I know the rating of this one? Right, I forgot this was not. That's kind of a good question. I would put it at like. Actually, wait, let me see. From the last div 2, the last div 2 had a very similar idea, and it's still not rated for some reason. By the way, a similar problem you can try is this one, paired payment from this round, 703E. So it'll be similar rating to that one, I guess. It's a bit easier. So whatever that one ends up being, maybe it's like in the like 1800 to like 2100 range or something like that. Oh, did I ignore you again? What did I ignore? How are you doing on this fine Wednesday? Decent. I'm streaming, so that's fun. Not much else to say. No, that's fine, yeah. It's just really loud on my phone for some reason. And you know I stream on Wednesdays, so it's like my thing. Oh, and by the way, I forgot to mention this at the beginning, but I did I put in the description? I did, yeah. So like this is a really cool way to look at graphs. Like you can just copy in the edges and it will just generate this graph for you. And you can just look at this and play around with it and get some really weird things on it. Yeah. But it's cool. It'll let you show things. So anyway, now we get to the implementation of dijkstras, and it's sort of fun. Sort of fun, sort of not. So let's do it. And also, by the way, I'm asking for the shortest paths from k different vertices, because I'm annoying. So let's read in the values. Then we read in the array. I'm not a speed demon. Oh wait, no, this is really easy to implement. Like you literally just, like all you do is just add an edge. Like you create a new node n, and then you add an edge from I to n with cost ai. That's it. And then run normal dijkstra. That's all you have to do for this special thing. Like my Polygon implementation is like 10 lines or something. Okay, so I need to remember how to implement dijkstra because yeah, you know, it's been a while since I've done this. But we're gonna create some edges. The graph is of size 10 to the 5th. By the way, what's the time limit mean to anyone? I want to see that actually. Hopefully the time limit is not a problem. That's not what I meant to click, but if I go to I, no, that's the wrong one. If I go to G, then we get TLE, but like, okay, MLE is fine because you can do it in nlog n memory, or you can do it in n memory. I made it 5 seconds just because, like, just to be nice. Yeah, see, this is another dijkstra one you can do. It's perfect. Okay, so LO dists. Alright, now so we're storing pairs. And then the edges is going to be the place that it goes to, and the wait. Oh my god, 25 accepted submissions. Jesus. Oh my god. That's so dumb. Okay, now so now, like, in the spirit of this, all we're going to do is we're going to add a new node n, and then add an edge from every node to n. Edges of I dot push back n ai. Let me also add an edge from every n to everything else. Yeah. So c into x. Okay. Now, might as well also increase n at this point, because now we have a new node. So dists I is equal to infinity, or rather, we'll use something like 1e18. Because the maximum cost is actually 2 times 10 to the 9th, which is fine, but no matter what, it's going to be not that big a deal. We can just use something large. So this I is equal to infinity. We don't need parents, so that's fine. What we do need is a priority queue. Like, I'm straight up forgetting how to do this. I think this is how you do it, right? So what this is basically doing, this is make a priority queue of pairs. But what these things are doing, it's basically making it so usually the priority queue gives you the largest possible value. But we want the minimum. We want the shortest possible thing. So one way we can do that is by, normally priority queue compares by using less than. But if we instead make it to compare using greater than, then it's sort of like setting all the values to be negative, because like everything's going to be in reverse. We use greater than to mean less than, so everything's going to be reversed. So it means that it's in fact going to give you the smallest value instead of the largest. But yeah, another way to do it is just simply to negativize the distance, and that way the largest value will be the value closest to 0, which is the smallest value. Oh yeah, and the reason we need the vector is just because like it's like the operator we use is the third argument. So this is like we can't we need this because it's the second argument, and we need to fill in the second argument. So the second argument just happens to be that. Yeah. Like you can't use greater because it's the third argument and you need the second to be filled in. It doesn't really mean anything in particular. That's just what the default would be. Okay, so we got some other stuff going on right now. What are we going to do? I don't remember. Alright, so the distance of the source is 0. Dists source is equal to 0. We can also do and like this I is equal to 0. Yeah, I mean, negativizing is fine. Either works. We need to create a template with save BFS. I have a dijkstra template myself. Like right in my code. I have this. And then like all I have is like a thing to initialize it, a thing to add an edge, and then you can run it from anything. And then what that does is that will like it just does it. And it makes it really easy because this is sort of annoying to code every time. So when I copy paste this in, like if I copy paste in my dijkstra template, I can solve this problem in like 2 minutes. It's just copy pasting it in. The code is so simple. So that's all it really is. Like my template will make all of this easy. And then all of this is free, like it's instant, I just copy it in. So all I really have to do is write this code, and it's so simple. This should be infinity. Wait, I did do that, right? You want it to be infinity because like it's storing the shortest possible distance. So if you can't reach somewhere yet, it means like it's not there. Yeah, like stuff like Usico, it's still a good idea to be able to implement things by hand, especially because it does show up a lot, stuff like dijkstra. So while not pq.empty, and we also have to insert this. So pq.push the pair, so it's distance 0, and then the source is the source itself. So pq.top, right? Like everything uses a different syntax for some reason. So if visited cur.second, which is the node, so like dist is equal to cur.first, targ equals cur.second. If visited target, then continue. Then yeah. Okay, now for each thing, for pair x, for each edge coming out from target, allow new dist is equal to dist plus x dot second. If new dist is less than the distance we have for the node that we're looking at, then we want to update that distance and put it back in the thing. Yeah, so if new dist is less than the distance of the current thing, what would that be? What am I looking for? So this is x dot first, because that's where the edge goes to. If new dist is less than that, then dist x dot first is equal to new dist. And we want to insert a new entry. If we have multiple entries for a current node, for one node, that's fine because we use visited anyway, so it's not that big a deal, because like we won't visit a node multiple times, and we'll still visit a node only when it's the shortest possible new path that we come up upon. So we add a new entry. It might like it's not that great for memory, but it's not really that big a deal either. If you need to save memory, then you could be a bit smarter about it and use a set and like erase things. Like if I update this, I would erase the previous entry, and that would save some memory. But in any case, it's not that big a deal. Maybe they would have it use at most O of vertices memory instead of O of edges, I guess. But here it's not a problem because the number of edges is equal to the number of vertices. So priority queue.push, the entry is the distance. So dist x dot first, and then x dot first itself, the new node. This should work. I don't know. I don't remember. I feel like I'm missing something, but I feel like I'm missing something. Yeah, priority queues have a much better constant factor because sets use like pointers and stuff, and heaps can operate on an array, so it's much nicer. Am I seriously not allowed to do that? Dists. Am I not allowed to do that? Cheeky.push. Invalid types long. Oh wait, is that what the problem is? Because I'm using dist instead of dists. Okay, cool. I made very strong samples just to be nice. It doesn't work at all. Doesn't even print anything. Well, that makes sense because I didn't actually do anything. So let's see. So now simply we run dijkstra from the source, then print the distances. Jesus, I almost flung my mic off the table. Usually I do that with my mouse, but that's not such a good thing to do with my microphone. Did that mess up the audio? I hope not. Okay, that's a problem. All right, interesting. So we get the first part because we don't want to do that. Otherwise, we ignore the entire graph, right? Okay, cool. We don't want to include the distance to n. That's not relevant. All right, 062, 604, 240. Yep, this sample's a bit stronger. 03. Yep. Try this one too because why not? It's very large, but yeah, it's fine. I trust it. It's rough. It's roughly the same. Yeah, but yeah, like I tried to say, and then sort of priority queue does have a better constant factor. Okay, so that is accepted. Again, another way to do it is to exploit the structure of dijkstra, and I explained that earlier, but that's sort of a more annoying way, so let's just avoid that for the rest of existence. Anyway, I think that was the only shortest path problem, unfortunately, so we'll get into things later. Okay, so that's G. Now we have H. So we'll mess this up. How slow is this chat? Do you see how slow it's updating now? It's like not even doing things. Like it's sending one message a second or something. Whatever you say, YouTube. I don't know why it's updating at one like unit a second, but whatever works. Okay. Is it fine? It's weird. Seems like I always pick the worst times to eat food because now I have to explain something. Okay, you have a connected undirected graph. Let's draw some stuff. Let's see, we got this. 1, 2, 5. 4 to 2 with cost 1. 2 to 3 with cost 2, 1 to 4 with cost 4, and 1 to 3 with cost 3. Okay, so here's how that works. You have an undirected graph with some weights, and basically the cost of the cost of a path between two vertices, like for example, say I take this path, is the maximum weight of the edge on it. So this would have weight 4, this would have weight 1, this would have weight 2. So the maximum weight is 4. Then the distance between any two vertices is the minimum of the maximum weights, is the idea. Yeah. So the shortest path between any two vertices is the shortest path. It's the minimum of all the maximum weights. So yeah. This is very related to minimum spanning trees. And the reason is because the argument is quite simple. Let's consider two vertices and find the shortest path between them. So we have an edge. So we have an edge with like cost 7. Okay. Now, the shortest path between them will be cost 7 if we don't have some other path with lower cost. So say we had some path with lower cost, right? Like say we had something like 4 and then like 2. Then it means that with using only the edges with smaller weights, these vertices would already be connected. They would be connected like this. So that this edge of cost 7 would be obsolete because we already have a better path to get from this vertex to the other one. So it's sort of like saying for every edge, it's relevant in the distance only if there's no better path. And like, so if we connect the components using all the edges of smaller cost, then like there's no better path there either. Wait, what am I saying? That's a good question of what am I saying? Maybe it's better to do this the other way. Let me explain how minimum spanning trees work, and then I'll relate that to this. Okay, so explain like the distance again. So basically, like for any path, it goes through a sequence of edges. And so the cost of a path is simply of all the weights, it's just the edge with the maximum weight. So the highest weight of any edge on that path. And then the shortest path between two vertices is like the same definition as the shortest path for dijkstras, just that the costs of the paths are the maximums instead of the sums. So really it's like the shortest path is simply the path with the shortest cost. It's the smallest cost. It's the same idea, but the cost is the maximum weight edge instead of the sum of the weights. Okay, I should get into what a minimum spanning tree is first. That's probably a good idea to do that in that order. So basically what a minimum spanning tree is you have a list of nodes. You have like a bunch of edges. Let's take some like, let's do 4, I guess. You have like a bunch of edges. Let's say you have this, 4, 1, 7. Does that work? Yeah. So basically what you want to do is you want to find a spanning tree. And a spanning tree is a tree that's like so now I have to explain what a tree is, but a spanning tree is basically a subset of the edges where there are at most m-1 edges, or there are exactly m-1 edges, and the subset of edges still connects the whole graph. That is like, if I take the graph with only the edges that I selected, it would still have to be connected. So for example, these. This is also a valid spanning tree. So for example, if I take 2, or if I take 3, 4, and 7, this is in fact the maximum spanning tree, then this is also a spanning tree because it's m-1 edges and it connects the whole graph. So a minimum spanning tree is simply a spanning tree that minimizes the sum of costs of the edges. That's its definition. The sum of costs of its edges. It also has some other cool properties, but let's not get into that for now. So the way to do it is simple. There are two algorithms I'm only going to explain one of them now, and then I'll explain the next one on the other problem. So this is Kruskal's algorithm for MSD. MST. Alright. I'm not going to prove it because I don't know how, but I'll just explain how it works. I think the proof is like inductive or something, but I don't really know how to do induction. It's like too smart for me, so I'll leave it be. Does it say the edges are distinct? No, it doesn't. Would be nice if they were, but I guess it doesn't matter. Yeah, but it's not easy to do for a graph because like induction on a graph. How do you even do that? Or maybe I'm mixing up the proofs. Maybe induction is dijkstra's, but the point is like I don't know. I don't really prove dijkstra's either. Dijkstra's, the argument's kind of simple. Like it's like if there's a better, actually never mind. Maybe I'll make tutorials on this in more detail, but this is sort of just an overview. It's like a survey course, so I'm not going to do proofs here. Let's reconstruct the same graph. So we have 2, 7, 4, 3. Just proving the correctness of Kruskal's, but I'm not going to do that. Unless there's an easy way to do it that I'm overlooking. But so basically the way Kruskal's works is you sort the edges. Then you go through them in increasing order. So we would have the edges 1, 2. So we have the edges with cost 1, 2, 3, 4, and 7. These are costs, not indices. Then we use DSU. Or we don't even need to use DSU necessarily, but we do use DSU. And what we do is we say, we look at this. So we look at the smallest edge, and we ask, if we add this edge, would it connect two nodes that are already connected? And if so, you ignore the edge, and if not, you include it. So for example, we would take this edge, then this edge of cost 2 would connect 2 nodes that are not connected, meaning that we should take this edge. And this edge of cost 3 would also connect 2 nodes that are not connected. And this edge of cost 4, well, these are already in the same component, so we would ignore this edge. We don't take it. And the edge of cost 7, same thing. So that's all it is. You go through the edges in increasing order or sorted order, and then you use DSU to figure out if the edge would merge 2 components or connect 2 nodes that are already in the same component, and you take it if they're in different ones. So the idea would be like, say we had an edge of cost like 5, for example. So that's how it relates. So how it relates to this problem is, say we have an edge of cost 5. Now this edge, yeah, I did explain DSU in problem E. I did explain DSU. I think it was E, yeah. So you can rewind there if you want. Sort of also like breeze through it, but it works, I think. I did prove the complexity of DSU. So if we have an edge of cost 5, I'm going to lose my voice soon. If we have an edge of cost 5, then I might get close to the mic and do some ASMR or something. If we have an edge of cost 5, then what happens is, if we take this, I'm drinking water. I've drank like 2 bottles now. If we don't take this edge, then it means that using only the edges with cost less than 5, we've already connected these 2 components. So in a similar manner to this problem, say we were asking, is the shortest path between 2 nodes 5? So like, for example, would we use this edge? And the answer is yes, only if we don't have some better path. So in the spirit of Kruskal's, if we're asking like, no, I'm not going to whisper. In the spirit of Kruskal's, if we're asking, can this be 5? We're asking, are these nodes in different components when we only consider the edges of cost less than 5? And if so, then that means there's no path between them with cost less than 5. And if they're in the same component, that means that using only edges of cost less than 5, this this edge is 5 can't be the answer because we can get there in better than 5. And then you notice that this sort of process, this sort of thinking, that if we can get there in shorter time, if we're already connected using a smaller vertex, if we're already connected using only edges of smaller cost, then it's basically the exact same thing as cross goals. So that leads to the observation that we only care about the minimum spanning tree. So really, for this graph, we're going to convert it to its minimum spanning tree. Like this. Like this. Like this. We're going to use 2, 3, and 1. So now we need to solve the problem on this spanning tree. So I haven't actually gone over the problem. I didn't even read the statement. Nice. But basically in the statement you have some special vertices. For example, 1, 2, and 3 is, yeah. You have some special vertices. And you basically want to figure out, for each special vertex, you want to find some other special vertex to maximize the distance between the two. This problem is quite involved. But for this special vertex, you want to find the other special vertex that maximizes the distance between the two. So now we sort of reverse it. We consider the edges in descending order. So let's consider the largest edge. Now, if all special vertices are on one side of this edge, so for example, say this wasn't a special vertex, then there's no way this edge could be part of the answer. Because if it is, then like somehow we would have to have a special vertex on this side, but we don't. Now, if we don't have any special vertices on both sides, then we're done. Or if all the special vertices are on one side, then we're done. I mean, we can't use that edge. Otherwise, basically, we can pick some special vertex on one side and some on the other. And then for every special vertex on this side, we can use the one on the other to connect that and then use this edge as the answer. Or we can use, for everything on this side, we can connect those to this one and use that as the other one. And then that would give us this answer as well. So we're looking for the largest possible edge that could be part of the answer, and the condition for checking if something can be part of the answer is simply, do we have special vertices on both sides? This is something we can compute by saying some edges like this, some edges like this, and then, no, I'm not doing that. That's going to be even harder. Some edges like this. And then we're saying in this blob on this side of the edge, do we have at least one special vertex? And in this blob, do we have at least one? And we can do this with tree DP. That was scary. And we can do this with tree DP. Alright, I forgot it's like nighttime for you guys, so it's even weirder. Yeah, I'm doing pretty well. No, I do not know who that person is. Look behind you. Yeah. Okay, so just do that some more. I don't know how loud that is. Like I know the mic like picks stuff up really well when it's close, but I don't know how that works. I'm very sidetracked. Sorry. Sorry to the people watching the VOD who are going to be annoyed by this again. So, Yeah, basically we can do this with tree DP. So we can compute for each node the number of special vertices that are under it, that are in its subtree. And then, like for an edge, we can figure out, like we look at the number of special vertices on one side, and the number of special vertices, let that be like x, and the number of special vertices on the other side is k minus x, where we have k total. And if both of these are greater than 1, then we're good, and otherwise we need to take some other edge. So we can do this with tree DP, basically. So that basically does it. Is there a better way to do it than other than tree DP? No? I don't know. So we're going to be let's see, how's this gonna work? So since I already implemented DSU on this stream, I'm gonna use my template this time. If you want to see where I did DSU, you can see problem E. Yeah. I'm going to try and silently eat lunch because it's like 1 now. Awesome. just ignoring chat for a bit since I want to not talk that much. I will respond to everything if necessary later. Is there music? I'm having this be a boolean, like, this is simply, if it made new components, then return 1. That means if it was included in the tree. And also edges x.s push. Oh wait, it's because I turned away my microphone to lower the sound, and then I realized that that also lowers the sound. So yeah. Okay, sorry. I made that boolean simply to return like if it merged successfully. So if it was a if it returns 0, then it doesn't merge components, and that means it shouldn't be taken in the tree because it didn't do anything, and otherwise then it's successful. Eating Korean food. It's called gyoza. Oh really? I thought there's like some Korean form of it. I don't know. Maybe some national pride. Maybe I'm wrong though. I don't honestly. I don't really know. That's all I know it is. assuming this works. Or not. Because I don't. Okay, 0, 0. Alright, let me actually respond to the chat, perhaps. That'd be nice to do that. Yeah, 17 years old, did a lot of CP, stuff like that. There's no OnlyFans, like, ever. No, not happening. Ever. No. 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 Just keep saying no until it goes away. If you want to learn, start with graphs. You can check the beginning of the stream. I'm not sure how good a job I did of explaining it, but I did try. Yes, I do know how to use chopsticks, mostly. Well, I don't have that much practice with them, so I'm not that great. And yeah, Wednesday I just don't have school for some weird reason. I don't know why they did that, but I'm not complaining. Okay, so I'm assuming DP is all 0, because that wouldn't make sense otherwise. Is Sophie a competitive coder? That is a good question. What? Why are all the edges 0? White is... Yeah, and no longer a YouTuber either. No, I live with my parents. I mean, like, I don't, yeah. X.F.F. What? X.S.S, X.F, right? Oh, wait. Why is that not working? DPV should be 2 here. Oh, wait, because I used the wrong array. That's why. I'm confusing myself with my own values. Should be 2, 2. Yep. It should be 3, 3, 3. Indeed it is. Okay. Do we have debug prints somewhere? We do, don't we? Yep, 3, 3, 3. Okay. Yeah, CMU is a pretty OR school, I would say. In fact, a very OR school. Being a prodigy is also pretty ORs. Anyway, let's submit. I guess values are 10 to the 5th. Everything looks good. Looks good. Yeah, I use Notepad++ just because it's a text editor. 73. Okay, that took a while. That took longer than it should have. Any thoughts on MIT? Yeah, it's quote unquote pretty good. I mean, it's like, yeah, quote unquote. Yeah, we're like across the US from each other, so that probably wouldn't happen. Alright, so you have an undirected graph consisting of n vertices, and a number is written on each vertex. The number on vertex I is ai. So look, this is this is where I stole G from. It's the same problem, but you have a spanning tree here instead of dijkstra here. So it's like, you know, number is written on each vertex. The number on vertex I is ai. You may add some edges on this graph, but you have to pay for them. The cost of adding edges is the sum of the values of the array. Interesting. There are also M special offers, each of them. So you have normal edges, and you can also add an edge for the cost of the sum of the two array values. Basically, that's how it works. It's the exact same as G, but you want a spanning tree instead of shortest paths. What is the minimum number of coins you have to spend to make the graph connected? So that is exactly what it is. What is the minimum number of coins, or what is the minimum cost, the minimum total cost to get a subgraph of a graph that makes it connected? That is the definition of a spanning tree, or a minimum spanning tree. MIT is our school next year. We'll see. We'll see. We'll see, maybe. Keep it at a maybe for now. Not really that concerned about where I go, though, so... Oh. What I should be concerned about is not forgetting to do this all the time. That would be ideal. Four-hour drive. That is a pretty long time. That's long enough for me to say that I don't want to do it, so therefore I don't want to do it. My threshold is like 4 seconds. If I can't drive there in 4 seconds, then it's not gonna work, unfortunately. Sorry, them's the rules. So yeah, let's draw this graph. God, that's a mess. Okay. Very similar sample to the one I had too. Or rather, my samples are similar. So basically, we have a graph. You can have some edges. So this is cost 3. This is cost 5. This is cost 1. Well, that's different. School is mandatory. This is like less mandatory. So my threshold is more strict. So you can take the normal edges, or you can also take any edge for the cost of the sum of the two array values. So you can have these edges. And you want to find the minimum spanning tree on this graph. So there are once again 2 ways to do this. One of them exploits the structure of Prim's algorithm. So Prim's algorithm, or Jarnik's algorithm, or whatever you want to call it. I know the USCO director, Brian Dean, is very picky about this, or what I know. So you can call it Prim's or Jarnik's, but everyone calls it Prim, so I'll do that too. The way Prim's works is essentially, it's actually extremely similar to dijkstra's. It's like basically the exact same thing. Like with dijkstra's, you maintain the set of the visited vertices, and you look at each other vertex, and you look at you look at the other vertices. Okay. You look at the other vertices, and what happened? Like, basically, with dijkstra's, you maintain like the distance it would require to reach each of them. Like for example, here and then 9 or something. Oh, there was a code shift going on? Maybe that explains the drop in viewership. Interesting. So, yeah, basically here you maintain the distance it would take to get here, and then for dijkstra's you greedily take the smallest one. For Prim's you do basically the exact same thing, except the distance is simply the cost of the edge it would take. So for example, say I do this, then this would have cost 7, this would have cost 3, this would have cost 2, this would have cost 1, right? So here, to get to this node, you can reach it with this edge of cost 1. You can reach it with this edge of cost 2. And so the minimum is 1. So the potential distance for this is 1. Here you can get from 3 to 3 or 7. So the potential distance here is 3. And here you can't reach it at all. So it's infinity. And then with prims, you just do the exact same thing. Oh, prims isn't shortest path. It's for minimum spanning tree. But with prims, you do the exact same thing, except the cost isn't the distance plus the weight of the edge. It's just the weight of the edge. And also with prims, you can start it at any arbitrary vertex, and it will work. So with that in mind, we can do the same casework we did with problem G, that either you take a normal edge or you take a special edge. So consider the set of unvisited vertices and the set of visited vertices. We can do normal prims to figure out what the costs are going to be for the normal edges. So for example, the minimum cost here would be 1. And say we have some array values like 1, 2, 3, 4, and 5. That's a 3 to clarify. So the cases are either we use a normal edge, which we handled, or we use a special edge. And for the special edge, we need to connect something that's in our node. We need to connect something that's in the set of visited to the set of unvisited. So the cost for doing so for some I and j will be ai plus aj. So the minimum thing we want is the minimum in here, the minimum ai from our set of visited cells, and the minimum aj from the set of unvisited cells. So once again, we can use a separate priority queue or something to maintain the smallest value of aj that we currently have, or a set, because you have to delete things. Or we can be smarter. We can be a bit smarter. Say we do prims, right? And then we just start it at the initial vertex. Right? So what that means is that, or no, we start it at the vertex that has the smallest value of ai. So what does that mean? Did I get rid of this code already? I did. We start at the vertex that has the minimum value of ai. So what does that mean, right? Well, it means that initially we would consider using the minimum value of ai for all possible cases of this in our cases. But because this is the minimum value, we don't care about any other possible value. This is already the minimum. This is already the smallest. So ai is constant. Let this be like x. Then we just need to minimize aj. We don't really care about minimizing aj. Like at every point, we're going to consider every possible aj as part of the answer. But the main idea here is that we're not using any source vertex for anything except for ai, except for this initial vertex we've chosen. So really, we only need to draw the edges from ai to every other vertex. And that's it. That's all we consider. So really, the only thing we need to do is we can stick in an extra n-1 edges, where each edge is from the node with the smallest value of ai to every other node with the cost of the sum of their array values. And because of the way prims works, because we can start at any vertex, if we start at this one, then those are the only edges we're ever going to consider. There exists an optimal spanning tree where those are the only edges we use. And therefore, we can assume that we're going to find that minimal spanning tree, and therefore we only use these edges. So really, what I'm saying here is if we draw things like this, for example, like that, and that, and this has, for example, 1, 2, 3, 4, and 5. The only special edges we have to consider are the ones that are adjacent to the smallest value. So this would have, for example, 3. This would have, for example, 5. This would have, for example, 6. This would have 4. And then we overlay the normal edges on top of this, and we run any spanning tree algorithm on this graph. and this would work. So that's it. That's all we do. So find the minimum, add these edges, run any spanning tree algorithm. It doesn't even have to be prims, because all we show is that there exists an optimal spanning tree with these edges. So really, I can actually use this exact same code for finding minimum spanning trees. So we just straight up do this. And then if AI, we're going to keep track of the minimum, is less than min v equals AI, min pos equals I. The fact that we add an edge from the minimum to itself doesn't matter, so we might as well do it anyway. So this is a cost of a min v plus AI, and then edge from the minimum position to I. So like that's it. We just run cross goals on this augmented graph where we add these special edges from the minimum array value to the everything else. And note that this has to be the minimum array value. It's not index 1, which just happens to coincide with the way I drew this test, but it has to be the minimum array value. Oh, come on. Alright, that wouldn't even make sense. What? Number of special. Alright, I didn't read any array values. Five. 16. 18. Okay. Sounds good. I mean, we just did basic cross goals, and it's like really simple. Like this is cross goals. This is cross goals with the DSU. That's it. So we should be good. That should handle it. Indeed it does. Okay. We have two problems left. One of them is easier, one of them is very hard. So we're going to have fun. We're going to have a lot of fun. Alright, we're going to have some implementation tricks going on here. Don't need spanning trees anymore, so we're done with those. Done with DSU, done with everything. Yes, I have pre-solved these, so I know what's going on here, but that's fine. Yeah, koala is the 2600, if I haven't made that clear enough yet. It's also a really cool problem. I have more to say about it, but not right now. So, this problem is interactive. And the way it works is you have a matrix. It's like barely graph theory, but like it still is, so it's fine. I mean, it's BFS. You have a matrix given to you as an annoying format. Or basically, you have a bunch of empty cells, like so. You have some block cells that are like so. Make them asterisks. You have a finishing cell, and that's it. You start in the position 1, 1. and you know that there exists some path from 1, 1 to the finishing cell. The only problem is what you have to do is you have to like the only problem is that, well, you can move in any of the 4 cardinal directions, but sometimes the cardinal directions were flipped. That is, like, if you say you want to go up, then it may take you down instead. This state of flipping is constant. That is like it doesn't change if you flip every time. It's like predetermined from the start. And also, if you go left, it may be flipped instead, and you may go right instead. So that's a problem, because if you ever end up on a cell with an obstacle, you will die, like, instantly. So you don't want to do that. And you want to figure out a way to do it so that you never die. So, yeah, this problem escalated very quickly. Pretty sure it's not as harsh. Yeah, you lose the game, but, you know, dying is more interesting. So, let's raise the stakes. Okay. I'm having a good time. All right. So how does this work? Well, first thing is, we know there exists a path from the starting point to the end. And the starting point is always the top left corner. Meaning that if there exists a path, we have to be able to move left, or we have to be able to move right or down, one of the two. Because if we can't, then how would we ever, like, there's no other way we can get to the ending point without going left, without going right or down. So the problem is that, like, if we go in the direction of a potentially unblocked, of a potentially killer cell, in either up or down, where we don't know where we're going yet, that could kill us. But the point is, one of these adjacent cells has to be free. And also, oh, by the way, when we make a move, we get the position. Like, we figure out, they tell us where we end up. So we can figure out whether it's flipped or not, and then from that, run like a BFS from here to find the path from here to every other node. So that part's fine. The only issue is we need to actually do it. So how do we do it? That is the question. And well, let's find out. Okay, so yeah, basically we only need to figure out if we're flipped or not. Everything else we can handle just doing standard BFS, since we have 2 times n times m queries, so we're fine. So we know one of the cells is free. Without loss of generality, let's assume that the right is free. Now, that means we're able to try this, because there's no danger of going left or right initially. We know that it won't kill us. So, yeah, we know that it won't kill us. So it's fine if we do that. So immediately we can figure out if we're dead on the... How does this work? Yeah, immediately we can figure out, like, if the left and right are swapped, or whichever direction we know is fine. So now that we know this, there are 2 cases. Either the finishing cell is on the top row, in which case we're done immediately. Let's just finish. Otherwise, otherwise it's not. And if it's not, then it means it's on some row below. Meaning that somehow, what we have to do is, well, somehow we have to figure out the bottom now. But if it's on some other row, it means that if all of these cells are blocked, if all the cells below this row are asterisks, then there's no way for us to get out of this row. So at least one of the cells below this row has to not be an asterisk. And that means that we can move to that cell, and then we can use that cell to figure out whether up and down are swapped. So that's the idea. Then once we figure that out, everything else is easy. We just run BFS from F and then produce the path. So that's how it works. Now we just need to do that, and the way to do that is to implement it. So we can, I guess, have different cases for whether this one is blocked or this one is blocked or something. Yeah, that basically handles it. Because again, you're guaranteed that there exists a path. So let's just do that. So we read in the N and M. Yeah. Finish eating lunch. Dude, why does this happen? Why do I thought the chat had froze again, but I didn't even see. Like, how did that happen? Why does this happen? I don't even know, because I know my no, I know my chat exists. It just freezes sometimes. I didn't even notice. Like on my, because I use my phone to read my chat as the stream's going on. But I don't know like how or why, or I don't know. Have I missed anything like significant? An interactive which is not binary search, yeah. For once. Yeah, you can self-advertise, Leo. I trust you enough. Yeah, it is overrated, true. This is a 2100, by the way. But it's not worth that much, for sure. Yeah, I'm 17, I'm in school. Right, I forgot I turned my microphone away again. Did you not hear any of that, or was it just quiet? If it was just quiet, that's fine. If it was inaudible, then I'm like annoyed even more now. But yeah, my chat froze again because like, why not, right? I don't know why it does that. Okay, just quiet is fine. Alright, let's do some implementation. Yeah, Whisper is not as good. Okay, so I don't really want to do this, but I guess we have to. Yeah, it should be good now. To save my throat, I'll stop talking for a bit. Yeah, for you guys who are leaving, see ya. Especially because time zones. And yeah, I prefer YouTube because, like, I mean, I do everything else on YouTube anyway. I can't really do screencasts on Twitch, so, or solution videos on Twitch, so it's just like easier to have everything in one place. I do have a Twitch channel, but like I barely use it. Like I've streamed twice on Twitch, and that's basically the extent of it. You can find it by clicking here on the channel links. The random comments, so those were ideas I took from last topic stream and forgot to do them. Global round, probably not because it's like too early and I don't really want to do it either. I will get back into rounds later, but I'm so far accustomed to doing them quite infrequently. How many problems do I solve a day? It's sort of an interesting question. On average, like 3 to 4. Well, actually, when I'm practicing, I try and do virtuals so it comes up to like 5 to 10-ish, depending on difficulty. Wait, but the way sleep works for me is like either I don't sleep enough and I do horribly, or I sleep fine in some range of fine that I don't... Mic is still turned. In some range of fine that I don't actually know about, and then, yeah, I realized. In some range of fine that I don't really know about, and then it's just like fine. But oftentimes it's just in the terrible range. Like it's black and white. There's no in between. It's either terrible or okay. If let's see, how does this work? So let me get the, is it row and column? The hell is XY? Let's go to the right, so it's row and column. Yeah, okay. So if we go left and it ends up in the same position, so if next is not equal to the current, then cur is equal to next, and swap moves 0, moves 1. So if m is equal to 1, so we're looking for if there's nothing below, if there's no cell below us that we can go to, then it means that the finish must be on the top. So we have to check that case, especially because otherwise we can't figure out whether we go down or not. So let's see. If we have exactly one row, then immediately it has to be at the top. Otherwise, we check everything in the next row. Why is my mic falling? Otherwise, we check everything in the next row. So actually, it's better to do this. If n is greater than 1, all I equals 0, I is less than n, I plus plus. If mat I, no, the second row, index 1, then the ith column is not equal to the finish, then at top is equal to 0. And then finish is going to be the method I described to say, finish is like we figured things out, so do BFS and finish the thing. Otherwise, I'm going to do some fancy math here. While pos.s is not equal to is the stream still going? It just said I disconnected from OBS. Are we fine? Guys, are we fine? I hope we're fine. I guess so. I mean, it didn't end. Okay, cool. Alright, that was weird. So anyway, well, yeah, slight disconnect. Okay, cool. I'm glad it doesn't like shut it down completely. Okay, so we're looking for, basically the way this works is we're at the top row. Should probably explain what I'm doing. We're at the top row, over here. We have some position down here that isn't blocked, so we're just gonna move to there. And then we can figure out whether the up or down is swapped. So while pos.s is not equal to down position, then what we do is we move with the moves of, so this is a bit hacky. If the position we want is to the left, then we're going to use move 0, and otherwise we're going to use moves 1. So it's going to be like that. Okay, why not? I'm gonna tell myself somehow. So if it's to the left, we're going to use move 0, and otherwise we're going to use move 1. Then we're going to move up. Alright, so now we know the direction of both, so we finish. Otherwise, we do basically the exact same thing on the other side, except it's like weird. So we know it's below. We know that we have at least one row. Wait, why is this equal? So let's fix everything. So we try moving up. If not, then that. Otherwise, it's at left. Right, pause, equal to 1. So if we're at the left, then yeah. So then this is I and then 1. And this should be M. And this should be N. I'm going to get some repercussions for copy pasting this, but I think we'll be fine. If M is greater than 1, for I equals 0 up to N. Wait, this should be asterisk also. This should be not blocked, not F. Yeah, so if M is greater than 1, for each thing on the second column, check if it's not blocked. If so, then we know somewhere. So this should be paused up first, the row. And then if right pause is lower, then we want to move up. Meaning that maybe it's better to do this instead. Is that going to screw me over? Shouldn't. Oh, I don't think it would. Doing math with booleans here. So if right pause is less, then that means we want to go up. So we would want to use up, moves 2. Otherwise, we don't. Now we try moving left. If it works, if it moves us, then we need to swap because it means we actually moved right. Now we finish. If we happen to finish and a move, then we're done. We just swap. We just stop, right? Yeah. Now we do some valid standard group stuff. Yeah, I'm gonna finish this mashup. That's the plan. Shouldn't take that much longer. I don't have much to explain about K. It's just kind of cool. Implement stuff. I do like to stream for a long time. Okay. Yeah, that was the thing. Just chatting? No, not after this. Not after this. Okay, wait. So, remember what I was doing. I can't even keep my train of thought enough to code. I need to get more endurance. That's what I'm doing these streams for, to practice endurance. I can't last a 5-hour ICPC contest. So for each, like run BFS from the Q pair LO. How will whispering help? that help him? I don't know how whispering would help me remember things. Seems like it would just take me off track. Alright, have fun. CS lab. X.S plus 1. Okay. It's basically just constructing the path to the end. For nr equals, it's basically the same code. Pos.f, pos.f. What's CG? I probably know what it is, but I'm not awake enough to think about it. Dist nr and c is less than dist of the current position, so we make a move that will decrease our distance. Oh, oh god. I'm not sure about that one. Maybe. I don't know. That doesn't sound fun, but maybe. No, I don't know who that is. He keeps saying that. I mean, I don't know him personally or anything. What is this? Where's NXT? 158. Oh, okay. Geometry is not fun. Geometry is not fun. No. Very not fun. Okay, I don't know how to test this, so. Alright, let's just do some things. 4-3. Okay, so it's asking for L, copy. Alright, let's do some things. So what do they say? This is where both of them are swapped. Okay, so this is, both of them are swapped. So we move to the left, which is actually to the right, so we move to 1, 2. Alright, so right is actually left, so we move to 1, 1. And we get an infinite loop. Epic. So what? What? We printed U. What happened then? Oh, I didn't put in the, okay, 4, 3. Yeah, I mean, the special cases and stuff like that are what makes it so terrible. So L will take us here. Down position is 2. Oh, I'm an idiot. Okay. If this is less, then I see. Alright. Oh god. Oh god. What the hell? Yeah, so L, 1, 2, 1, 3, 1, 3. What? Come on. What's happening now? So 1, 2, 0, 2. Oh, that's why. Wait, what? How the hell am I getting to 0? Oh wait, no, that's what am I saying? Should be the column, right? So we're at column. How is pos.s that? Oh my god, because I'm using the wrong thing. That would make sense. So I'm using the wrong variable, which makes sense. So this should all be cur. Alright, this is stupid. using my very confusing notation here. Does that fix things? Probably not, but try it anyway. I thought I did answer that before though. Maybe I didn't say it clearly or something. 1, 2, 1, 3. There we go, finally. So 1, 3, U is down, so that gives us 2, 3. So we go right now, and that moves us into the obstacle. Okay, so what the hell is the point of that? Oh, because I didn't. Right, kind of have to avoid obstacles with the BFS. Probably a good idea. So 1, 2, 1, 3, 2, 3. Okay, still R. Guess I should avoid that too. Because otherwise it's 0, so that doesn't make sense. 1, 2, 1, 3, 2, 3, 3, 3, 4, 3, 4, 2. Finally. Okay. Try the transpose. 3, 4, dot, star, F, dot, star, 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 dot, 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 dot. Alright, U. So that gives us, everything's flipped, so everything's flipped, so that means we're at row 2. Row 3. So we try L, moves us that way. 2, 4, 1, 4, 1, 3. Epic. Okay. Guess it's worth trying. It's a mashup. Can't hurt that much if we get a wrong answer. Can't hurt that much, right? Why not? Try both cases. I mean, seems like finish is working. Maybe we can try the case where we have this. Let's try this. So 3, 2, and something like dot F dot dot star. No, star star dot. That means we should finish early. So 2, 3. So we try U. Why do we try U? important thing to note. So we try L, 1, 1, and 2. Okay. So it should be good. Test out the case where we don't have anything here. And we just hit the 5-hour mark. Nice. So L, 1, 1, and 2, and 3. Okay. All right. Try it. Try it. Try it. Try it. Try it. Try it. Bit of a pain to implement. I assume we'll get wrong answer here. Or some other weird verdict. Okay, well, that's unfortunate. Guess we use this time to look for bugs. Is it idleness limit exceed or something? So read in the values, read in the matrix, find the F position. Fine. Just give me the verdict already. Come on. Why does it run it like 12 different times? Okay, so if we have at least one row, or at least one column, and it's not blocked, then move to the here. Try moving left. If it doesn't work, or if it moves us, then it means we're inverted, so swap left and right. Then we're at the top. Time limit exceeded. That's even weirder. For at the top, it's 1. And we store the position. Right, now while we're not there, move to there. Try something simple like this. 2, 2, 2, dot, dot, F star. So L, 1, 2, 1, 1. Okay. Yeah, TLE2, I know. Cur equals move that. I mean, it does work in that direction. Next equals move U. If we're not at the current position, yeah, just try doing things. Okay. If we're not at the current position, swap the 2. Yep, same exact thing. Then we check and we check if we have more than one column. We check the column to the right to find something that's not a star, and if so, then we equals I. So if we're at the left, then finish. Otherwise, two plus this. So if right pause is less, then we would move up. And up is this one wrong? So right pause, why did I do this? Right pause is less, then this will be false, so it means we're moving in the up direction. Yeah. Then otherwise, so is in the finish that's the problem? I guess that must be it. So Q. Okay, so if we get a -1, then it means it's invalid. So I guess we can try that. And so okay, let's try that. So we put in the break condition and see if it's invalid. Okay, so it is somehow invalid. Okay, so it's not TLE, it's just getting into the bad position. Right, so how does that happen? Is it somehow we're moving into a dead? What would I be messing up then? Pair. X equals q dot front, q dot pop, p equals x dot f. If we visited this, continue, otherwise have the distance be that. Now if this is not a star and we can go here and we're good, then do it. And try moving in a place that decreases our distance. So what would that kill? What would I be missing here? Is there some other edge case that's happening? It's not getting caught in the while loop, it's hitting an asterisk. Just a different problem. Am I running out of moves? Is it hitting an asterisk or getting stuck? Let's try some weirdness like this. 5, 5. Or 5, 6. I don't know what to do. Star, 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 dot, star, dot star, no, wait, dot 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 star f star dot 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 dot. I don't know what that would do, but why is it not? Why is it not reading anything? What? What happened here? Wait up, what is it doing? This is not even reading in stuff. That doesn't make sense. Why did it not read in the value? So we have n equals 5, m equals 6. What's happening? Like, is it printing something and not... Why would that do something? Where is it? Where are we right now? What's happening? Should get here. Why are we stuck? So it gets to here. Like, in what? Fourth column only is. Oh wait, I saw the rows and column. Why do I always do this? Okay, that's. I don't even get why that would happen, but. Wait, now this doesn't even have to go anywhere. I see why that input is wrong, but I don't think it should make a difference. What is happening? Okay, so it gets here. Oh wait, I was waiting for my input, that's why. Okay, I guess that fixed it. How did that break it though? I'm dumb, I forgot. Forgot it was interactive. So that would kind of change things. Okay, so what? So there are no swaps. No swaps whatsoever. So 1 1 1 2 1 3 1 4 1 5. So try going up. 1 5 again. 2 5 3 5 3 4. Oh, wait, I gave it the wrong. Give it the wrong output. Yeah, this problem is indeed annoying. I want to solve K. I want to implement K. I have an hour. I have to cut the stream off at 4 because I have something else to do then, but I'll see if I can get K by then. Okay, wait. Let's just finish this input. I don't know why it crashes when that happens, though. 1 1 1 2 1 3 1 4 1 5 1 5 2, 5, 3, 5, 3, 4, 3, 3, 2, 4, 3. Okay, so that's when it ends. So make this blocked off now. What does that do? Just don't know why it would break like that. So it tries U, 1, 1. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 6, 1, 6, 2, 6, 3, 5, 5, 4, 5, 3, 5, 3, 4, 3, 3, 4, 3. Does find it right then. Did I test this correctly? I shouldn't have chosen this problem. Okay, 1, 1, 1, 2, 2, 1, 3, 1, 4, 1. Interesting. Let's try this. So 1, 1, and 2, and 3, 4. Ah, I see the problem. Okay, that's why that would happen. So I do want to break here. That should fix it. There we go. Okay. So the problem was that, so what I was doing was I was looking for a cell on the next row that like we can use to test, for example, the up and the down. But the problem was that I was doing some extra voodoo stuff, and it was like it was possible that like this could be blocked. But we would still, this could be blocked, but we would still, yeah, like, because it would by default take the rightmost, so that would be a problem because it would try and move through this asterisk and that would kill it, but if we did this instead, it would work. So yeah, that's fun. Okay. Just so happened that the sample didn't have that case. Alright. Time for K. We have an hour left. Like I said, I have to cut the stream off at 4, so hopefully we'll be done by then. Oh, come on. Anyway, that was just figure out the directions, then do BFS to figure out the path. Some stuff involved. Okay. So I am sad about this because I did have this problem spoiled because it was like an old problem and I read the editorial for it because I was like mad about the rest of the contest, but it's still cool. So the way this problem works is I can pin the thing first. Current problem is K. And that is the last problem. And this is a very hard problem. So, or it's like difficulty wise, it's a lot higher. So, like it's an F. So koala land consists of M bidirectional roads connecting n cities. You have a graph, roads are numbered, etc. Start from city 1. When you move, you write the number down. So say you have a thing like this. And then the labels are like 1, 3, and 2. Then this path would literally just be the number 1, 3, 2. You concatenate the numbers to make it work. And you're interested in the shortest path from 1 to each vertex where the cost is the concatenation of the numbers. So the problem is that we have multiple digits. For example, something could have label like 17, and then it would be weird because there's no great way to compare huge numbers. But if we did something like assuming that all the numbers had like one digit, what the hell? Using my writing tablet as a mouse pad, which like makes like negative sense. So just using the, okay, whatever. So assume like the whole graph only had one digit edges. We can basically just do like a sort of like greedy like BFS kind of thing, because we know that the earlier, that doesn't, okay, I don't know what I'm drawing here, but make this, sure. So the earlier numbers like have more precedence. So we break ties first by the earlier numbers and then by the later ones. So say we had something like this, then we would want to visit this before that. And then like say we had like 3 and then 4 and then 1 and then 2 and then 5 and then 6. Then what we would do is, in the order that we initially had in the queue, we know that the queue is going to order the numbers by their values because we're visiting them like greedily, sort of. So now going here, we once again do the same sort of greedy where we look at the earlier values first and then the later ones. And then here we look at the earlier values first and then the later ones. And then here we would do the same thing. So, yeah, that'll be the way it works. Problem is if we have ties, that it's sort of weird that we have to like, because like for a particular node, like so, actually wait, let's say we're interested in, for example, this graph. Where this is our starting position. Then we have like 2 1s here, and then like a 2, and then a 3, and then a 1, and then a 5, and then like whatever these are. All right, so the problem is that like we have this and we have this, but if we start here, then we get an inherently worse path than when we start here, but we don't know how to break ties yet. So that's sort of the problem. We don't know how to break ties here. So instead of breaking ties, we just like group everything that's the same in one. So we would store both of these positions in the same state in the queue. So the like for a BFS, the state will be like the vector of like all the tied first positions. And the value. And the value mod 10 to the 9th plus 7. Yeah, also we have to compute the values mod 10 to the 9th plus 7 because they can be huge. But we have to maximize not the remainder, but the number itself. So like you have to solve the problem. It's like the remainder of the minimum possible number, not the minimum possible remainder. So yeah, the problem is they aren't all one digit, but we can remedy that by doing a bit of magic, where we can once again create some fancy virtual nodes. Like say this was this. We can instead just convert it to a new graph where everything is one digit instead. It's like for example like this. It has to be directed because the order is important. And then we could do this. And then at the same time, there's a subtask? What's m equals 20? Oh, is that something else? And then we make the same graph here, and then this would simulate this bidirectional edge. Wait, it's connected. Yeah, and bidirectional roads. So this would be 1, 3, 7, 2, 6, and that way it's still like the same graph, but everything's one edge, and the only way to get from this one to this one is by taking pen work? The only way to get from this one to this one using this edge would be to directly take this, because these nodes have no access to the outside world. When you go along this node, you have to go along the rest to be able to continue. So that's the idea. Basically, we break multiple digit numbers into single digit ones. And then we do some sort of greedy like BFS thing. And my mouse is dead. Is everything dying? My phone is dying, that's for sure. Alright, see if we can implement this in a few minutes. Where is my mouse actually just... Oh, wait, okay. I forgot I left my pen on the writing tablet, so it was holding the mouse in one position. I didn't even notice. Done that many times. Okay, so okay, so cur is like the pointer to the virtual node we need. So we need m times up to m log m, so 1,000,000 should be fine. Create a try of all the smallest numbers so far and then dynamically update LCA in the try. Would that be valid? I guess each thing only adds one possible node. That's kind of cool, actually. Yeah. I guess that would work. Interesting. That is pretty cool, actually. Hard, but cool. Alright. So... Oh wait, there is no z. Z equals I plus 1. So while z has more than one digit, then actually, let's do something better. And we can do something like add x, y, I plus 1, add y, x, I plus 1. So while z is greater than or equal to 10, edges targ dot push back we go backwards. Target is equal to z. So this should be cur, and then we create that new node. It just cur dot push back what? So it'd be z blanking here. We'll create a new edge from a virtual node to target, and then it would be z mod 10. Then we add an edge from x, which this target should be y, dot push back targ z. Cool. So now we start a queue of vectors. This is kind of weird. Will this syntax work? That'd be cool if it did. Okay, fine. Wait, so we need to start from there. Okay. Oh, push. Is that what the problem is? What also gives it different problems? So don't need to actually run it yet. So while not queue.empty plus cur time. All right, so this is going to represent each digit. Now, so wait, so this would be 4 y x dot f. What did I call it? Dist y is equal to x dot s. Will this kill me with memory? No, it's fine. How is this gonna work? I need to like do some weird stuff without like resetting everything. So if touch Z is equal to curve time. This is saying, have we touched it in this iteration of the queue? Then best Z equals min best Z. In fact, this should be a pair. Yeah, I'm tired, but that's how it gets sometimes. You have to go for long contests. I mean, ICPC is 5 hours. That's how it's supposed to be. IOI too. So we do the same thing here, except now. Else touched Z.F equals current time. Best Z.F equals Z.S. So now here, if touch Z.F is not equal to current time, now how does this work? At Z.S dot push back. No, it's not Z.S. It's at best Z.F back Z.F. Yeah. If this y don't revisit things. Ignore that too. Push. What is this? So this is x.s times 10 plus I mod. That's the new cost. We just stick on this digit at the end. Right. So now we are going to fix something that I forgot what we were gonna do. All right, fix the mod. All right, let's see. Should do it. And use variable z. It's fine. That's wrong. Okay. How's it get that so wrong so quickly? Yeah, I'll be done after this stream for a while. I have a meeting at 4, but then it's gonna not doing much else today. That would be the plan. I mean, I usually do it for this long. It's not like I'm not used to it by now. Okay, right, so somehow that's messed up. I'm allowed to print this, that's fine. So that's 10. Wait, why is it not making this a thing? You have 11 nodes. Oh, that's why. Because I just ignored that. makes even less sense. Yeah, okay. Otherwise I wouldn't even get there. Cool. There we go. 1210, 121011. Yep. One two one 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 two one three 1 3 4 1 3 4 5 5 6. Okay, looks right. I don't want to test anymore. If we get wrong answer, so be it. If we don't, awesome. Wrong answer in test 1. What? Oh. Whoops. Didn't even notice that was there. There we go. Looks like it's passing some stuff. Is this gonna fail system test on this problem? Time limit exceeded. Okay. What's with that? If I cheat and raise the time limit, will that fix it, or is it like an actual problem? Is it the fact that they're vectors? Alright, that's just annoying. That would have failed system test too, wouldn't it? God damn. It's rather annoying. So why does that die? What's happening here? Get rid of the vectors, I guess. So wait, at size best c dot f. Size I. Does this work? Just getting rid of vectors because didn't seem to like those. still works on everything. Alright, so if we get TLE again, then that means it's worse than a constant factor, which would be a problem. It shouldn't be n squared, but it might be? I don't know why it would be. I guess we're getting TLE again. Okay, what's with that? So, doesn't seem like it would be a constant factor off. So I'm messing something up. If you go here, while this queue is not empty, so we don't look at things that have already been visited. Oh, wait, maybe that's the problem. This point penalty is less important. Let's just finish this problem and be done. And the amount of problems I've failed system tests on recently, it's like disappointing. Yeah, the problem was that we could still potentially go through the edges of a vertex more than once, and so that would kill it. Okay. Well, that does it. That is all of the things. So you're getting TLE? Or wrong answer. Interesting. Okay, yeah, that was graphs. If you like the stream, I don't know, do whatever. Yeah, let's see. So everything's gonna be available afterwards. I'll do timestamps like soon. And then yeah, everything will be available on YouTube shortly. As like an archive or whatever. Alright. You can check out Leor's stream if you want. I forgot what the link is, but have a nice life. Yeah, you can scroll up a bit to find Leor's stream. Okay, goodbye.